We're going to start from setting up our work environment. If you already have Linux installed, then you can skip to the good part, the tips and tricks section. The first software we need to install is VirtualBox. It's a management tool for local virtual machines. So we go to a search engine and type in there VirtualBox download. And the very first link is the one we need, as it leads us to the official VirtualBox website, virtualbox.org. We click on that link to move right to the download page of the website. Here we can see all the possible download options for different operating systems. Ours is Windows, so we click on the first link. Then starts the downloading process. After it finishes, we launch the executable file that has just been downloaded. We easily go through the setup steps in a way like next, next, finish. And the VirtualBox window will show up in the end. We're going to leave it for a while until we download Linux Ubuntu, which we are about to install. So we switch to our browser and make new search request, which is Ubuntu download. The first link, which leads us to ubuntu.com website, is the one we need. So we move to official Ubuntu website. Here we scroll until big green download button. But before we press it, let's discuss the recommended system requirements listed on this page. So, it's 2 GHz dual-core processor, or better, 4 GB of RAM, 25 GB of disk space. But in fact, if you're going to use Linux Ubuntu for study cases only, you might reduce these requirements by 50%. A little life hack from a teacher. Anyway, we press the download button to get an ISO image of the latest Ubuntu. Keep in mind that this file is quite heavy, several gigabytes, so it can take some time to download it. When it's done, we switch to VirtualBox window to create our brand new virtual machine. So here we go to the machine menu and pick the new option. Then we fill in a pop-up window fields, virtual machine name and folder where its files will be located. Please note that the chosen hard disk has to have at least 20 GB of free space. As we mentioned the Ubuntu word in the name field, the VirtualBox interface automatically filled in for us the type and version drop-down lists with appropriate values. We press next to go to the further step of virtual machine creation. Here we choose the amount of RAM and the number of CPUs. As we saw on the web page, the recommended amount of memory is 4 GB. But for our study cases, 2 gigs is also enough. So let's pick 2 processors for better performance during the installation process at least. And let it better be 4 GB of memory. Click next. In the next step, we define the amount of disk space that our machine will use. Make sure you have that amount of gigabytes on your disk drive. We will leave the recommended amount as the interface offers us. In the next step, we can check all the options we have set for the machine that we are about to create. If everything is okay, we click Finish. And our virtual machine itself has been created. But it's empty, so there is no any Linux yet. And to set it up, we have to install Linux from the downloaded ISO image. So we do the right mouse click to enter virtual machine settings. In the settings pop-up window, we pick the storage in the left menu. Within the storage devices list, we need the one with compact disk logo and the title empty. And now by pressing the disk sign on the right, we choose an ISO image of Linux Ubuntu that we downloaded before. Now most likely our virtual machine will get started automatically. If it doesn't happen, we can double click its icon on the left. Now we will go through the steps of Ubuntu installation process. It's pretty similar to Windows installation, but if you haven't done anything the same before, don't be afraid, there's no black magic. Every step is pretty reasonable. Now we pick the first option, try and install Ubuntu, in the black window menu, and wait a little for the installation process to start. In the welcome step we choose install Ubuntu. In the next keyboard layout step, we can choose the preferred language and keyboard layout. We're leaving here everything as it is, i.e. English by default. Click continue. Here I would recommend picking minimal installation, so that it doesn't include a lot of software we don't need for our study case. But it's up to you. Click Continue and Install Now. Confirm by pressing Continue again. The next step offers us to choose the time zone, but usually the one it defines itself is suitable. Now we're going to fill in a username, computer name, and a password to login. I would also tick the checkbox Login automatically, so that it doesn't ask us after each reboot. Click Continue and go get some coffee, as this process will definitely take some time. We will fast forward it to save your time. It offers us to restart, we agree. Okay, great. Now it's our first launch. Probably Ubuntu will offer you some first setup. If you want to, you can go through it or click Quit. Our goal is to launch the terminal. So we press All Programs button down in the bottom corner and type Terminal in the text box. Then we pick the icon it offers us and bingo, here it is, our terminal. This is the window we are going to spend all our course in. On the taskbar we can remove the icons we don't need, and it could be convenient to add to favorites our terminal window. By default, Ubuntu checks for updates periodically and offers us to install them as well. If it shows the window about it, we can press Install Now button. Update process though can take some time too. Most likely we will have to reboot again. And one more final step before starting using our brand new Linux Ubuntu. It is recommended to install so-called guest additions. It is a piece of software intended to ease our life in virtual machine. For example, it helps seamless mouse movements between host OS and virtual machine. So, to install them, we go to Devices menu. Here we pick the last option, Insert Guest Additions to the image. If it doesn't automatically open a window to initiate installation, then we manually press the CD icon on the taskbar and in the open folder find autorun.sh file, right-click and pick Run as Program menu option. It might ask us to enter our user password. We do it and everything else will be done automatically for us. Now we finally can open the terminal window again and start enjoying the process of learning Linux terminal. So let's dive in. In this section, we installed VirtualBox, the manager of local virtual machines. We installed the Linux Ubuntu operating system and launched Linux Terminal, our work environment for this course. So now we're gonna learn some terminal tips and tricks to improve our productivity and to become way more efficient and probably even compared to our older colleagues. For example, if we see that our terminal is overloaded with different info we would like to get rid of, we can do it by clear command. We type clear and press enter. So we can see our terminal is clean now. And there is a hotkey for this command as well. We're going to create some mess here again to demonstrate it. Then we press Ctrl L and we can see the same result as after clear command. But in fact it doesn't really clean anything, because we can scroll the result back after this command and all the previous commands are back on our screen, huh? The next useful hotkey is Ctrl U, which helps us clear everything to the left from cursor. Let's type some long line and then press Ctrl U. Once again, look, if we place the cursor somewhere in the midst of the line and then press Ctrl U, we only get rid of the left part of the text. To clear everything to the right from the cursor, we press Ctrl key. So Ctrl U clears text to the left, Ctrl key clears text to the right. One more useful command for cases like these is reset. It can help us fix the screen output when it gets a little bit broken. For example, when we outputted some specific non-displayable file symbols. So reset, enter, and our terminal look is as fresh as new. Now we will take a look at different options to find help for our commands. The first way is typing what is before the required command, like what is clear. This always shows us one-line description for the command. Now we can read that clear command is used to clear the terminal screen. Or what is history, to show one-line help for history command. Or what is reset. The other option is help command, like help history. This way we see more detailed description of the command. Or help cd, to see some info about cd command. One more way to show command description is -- help option typed after command, like history -- help. As well, there is man command, which is, by the way, a reduction for the word manual. So if we type man clear, for example, then we will see the most detailed description for the clear command. We're gonna scroll down here because there is a lot of text. To exit this help page, we can press the Q button on the keyboard, which is hinted at the screen bottom, by the way. Also, I would like to draw your attention to the letter case importance in Linux. So we type commands only in lowercase. You can see that man command in uppercase won't work. We can see the error text command not found, while man in lowercase works just fine. Similar to the man command, there is info command. You can use this one searching for help as well. If we forget the certain name of the command we want to use, then we can start typing its name, the part that we remember at least, and then press tab key twice. Like this. We type hi for history and then tab. And now we can see options that our terminal offers us for the commands starting from HI symbols. And the last option we're going to take a look at is apropos command, which can be useful for the case when we forgot the exact name for some command. Like this, apropos his. Enter, and then we see all the available similar looking commands. We have already used the history command, so let's talk about it in detail. This command allows us to look back at the list of the commands we recently used. As one of the history command arguments, we can use a number, which means limitation of the commands we want to see. Like history 5 or history 10, so that we see only the required number of recent commands. As you might have noticed, every line in history command output starts with a number. This number can be used to address certain command from this list. We can do it using exclamation mark. For example, exclamation mark 37 to run the 37th command again, which is man clear command, to bring out to the screen manual for the clear command. Remember the Q key to get back to the terminal command line. One more case to use history is the double exclamation mark command. Using it, we can run the previous command. Also, we can use exclamation mark like this. Exclamation mark -6 to run the 6th command from the tail of the list. In our case, this is gonna be man clear. And here it is. If we want to search within the history of used commands, we can press Ctrl R and start typing needed command. The terminal will then show us available options. We press Tab to use the chosen one and the command gets run. Let's take a look at a few more tricks with history. We can clean commands history by typing history-c. Then we will output actual history and find nothing that was there before. Now we're gonna run some random commands to create new history. Check it out. Here it is, brand new. there is a possibility to hide some command from history. Ordinarily, every executed command goes to history, like we run ls and then can find it in history. But if before execution of some command we put a space in front of it, then it will not go to history. See that cd/ command hasn't been written down in history. This is how this trick works. So in this section we have covered the next topics: some useful terminal hotkeys, getting help for commands, and working with commands history. The current directory path can be shown using pwd command, which stands for print working directory. On the screen you can see that our current location is /home/itguy, which means that there is the home directory in the root of the file system, and within it there is an itguy directory. To change our location in the Linux file system, we can use the cd command, and surprise surprise, cd stands for change directory. We can use it like this: cd/home, and this will bring us to the root home directory. pwd output proves that. We can get back to itguy directory by typing cd itguy, and we're there. And there's an option to move to the parent directory, I mean parent to our current location. So if we type cd ... then we will end up in /home directory, because /home is the parent to /home/itguy. So in any Linux path, the slash is the symbol that divides folders' names. We can type cd ... again, and this will mean that we will go to the very root of the file system, which is denoted by the slash symbol itself. If we try moving to the parent directory from the root folder, which is slash, this will not bring us anywhere else, because there is no parent for the slash, and this action is not causing any error as well. There is a tilde sign in the Linux file system. It means the home directory for the current user. So if we type cd tilde, meaning that I want to go to my home directory, I will end up in /home/itguy, because I'm working now from a user named itguy, and that folder is his home directory. Also, we can change our location like this: //war, for example, which is going to move us 2 times to the parent directory and then to the var folder. And let's see where we are. /var. cd- command can move us back to the previous location. So we're now in our home folder. If we type cd- again, then we will go to the /var folder back. Let's move to our user's home directory by typing its full path: /home/itguy. In general, there are 2 ways to write the target path for the cd command. Starting from /, this is called an absolute path, and starting from whatever else, it is a relative path. The difference between these 2 types of path is that using an absolute path, we don't care about our current location at all, while typing a relative path, it's being formed based on the current location. Now let's discuss our folder's content. There is ls command, which shows us files and subfolders within the current or specified location. So typing just ls will output to us the current folder content. We're now in our user's home directory, and those outputted blue titles are the names of subfolders. Look what's interesting: if we add -a key to the ls command, then we can see many more lines in the output. The reason is that hidden files and folders have been added to the output by that -a key. Also, we can notice that those added files and folders start from dot. The idea is that in Linux, to make a file hidden, you just start its name from dot. So neat, huh? The ls command also has -l key, which changes the output to the look like this. See, now we have a table view of the folder content, and file names here are only in the last column. In addition, we can use these keys in the ls command together, like ls-la or ls-al or ls-a-l or ls-l-a. All these commands will output for us the same result, which is both .table view and includes hidden files and folders. So far, we outputted the content of the current directory only, but we can specify the folder path that we want to see, like ls/var, to see what is there within the /var folder. The option to use specific keys to change our output is still there as well. So we can add -l key to have table view or -a key for hidden files. In general, the ls command can have a folder specified for output and some keys to change the output look. By the way, our Linux Ubuntu has one alias for ls-la command. It is ll command. We can see that output of these two commands is pretty much the same. So ll command is an alias for ls used with -a-l keys. So in this section we've covered the topic of basic navigation commands, such as pwd command, cd command, ls and its alias ll command. For creating folders in Linux, we use mkdir command, which is usually pronounced as makedir. So we type makedir, then folder name, enter, and here's a new folder which we named Linux course. ll or ls commands can be used to check the result. Let's move into our new folder by the already known cd command. Of course, our folder is empty as we haven't created anything there yet. By the way, a little comment on ll command. You might have noticed that the output of the ll or ls-la commands always starts from two lines. The first ends with a dot, the second ends with two dots. So the first line ending with a dot contains the info about the current folder where we are located now. And the second line, which ends with two dots, is the parent folder for our current one. There is also the option to create multiple folders by one command. So we can type something like makedir folder1 space folder2 space folder3 and see all these three folders being created at once. One more specific thing about the Linux file system. Look, we're going to create a new folder named folder1, which name starts from the upper F symbol, although we already have a folder with the same name, just with the lower first letter case. So the idea is that for Linux, these two file or folder names are different, which is not the same in Windows. Because in Windows, we couldn't have created these folder1 and folder1, where names differ only with the letter case. Another way to use makedir command is this. We type makedir2/3/4, meaning that we are about to create nested folders at once. It didn't work this time because this trick needs the -p key. When we add it to the end of the command, then something gets created. Let's check it out. There is the 2 folder here that has just been created. If we go into it, then we will find one more folder named 3. Let's go into it and surprise, surprise, there's folder named 4. So we have created the hierarchy of folders using the / symbol between folder names in one command. It is suitable here to mention one more useful command, which is called tree. If we type tree and see the answer like command not found, this means that we can install it by the command written 2 lines below. I mean sudo apt install tree. So we just copy and paste this command or type it by hand and it'll install the tree for us. A little program that outputs folder structure in a convenient way. But before we use it, let's move several levels up in the file structure. Guess where we will end up if we type now cd ... huh? So it'll move us 3 levels up, and we're now in the Linux course directory. The pwd command proves that. Getting back to the tree command, it shows us the folder structure. Now we see all the folders we have created. Directory 2 containing directory number 3 containing directory 4. And other flat folders, located on the same level. Let's discuss one more case you might encounter while creating a folder. So, we're up to create some new folder. Press enter and get this permission denied error. If that happens, first make sure you're creating the folder in the right location. Supposedly, we're sure of what we do. Then we need to claim the admin rights for our command. We do it by the sudo prefix for the previous command. So we add sudo run command and it works just fine. But when we check the result, there's no folder that we have created. Where is it? It is located not in the current location, but in the root of the file system, as our path for creation of the folder started with the / symbol. So we will find our folder in the place where we put it, in the root of the file system. In Linux, there's definitely more than one way to create a file. And now we're going to discuss this topic. The first way to create file is using touch command. So we type touch, then the name of the file, and here it is. The next our option is echo command, with the greater than sign and followed by file name. So the new file has been created as well. Also, we might omit the echo command. Just greater than sign with the new file name creates it as well. Probably you have noticed that the last new file 3 has no extension. We did it intentionally. I wanted to draw your attention to the idea that in Linux file extension doesn't have that huge importance as it does in Windows, for example. So here can exist a lot of files without extension at all. They can be images, scripts, other executional files, etc. And it's okay, because Linux doesn't care about file extension if only for users' convenience. And the last way to create file that we're going to discuss now is the cat command. It looks this way. We type cat, greater than sign, and file name. After we press enter, the terminal is waiting for input from us. Everything we type now goes to the file content, and it'll continue until we press Ctrl D. Then input finishes, we get our command line back and we check the result, so a new file is here, and within it there's a text we entered just now. I wanted to pay a bit more attention to the touch command we used in this section. So this command allowed us to create a new file. But if we use this command followed by the existing name of the file, what will happen then? In this case, the date of the file is gonna get updated. So we input again touch and new file 1.txt, and we know that this file already exists. Now we can see that the date of the file has been updated. Just the date, and nothing else has happened to that file. So this is how touch command works with existing files. So in this section we discussed commands used for files and folders creation, such as makedir command, touch, echo, and cat commands. We copy files in Linux by using cp command. Let's take a look at files we currently have in our directory. We're going to copy some of them. Let it be new file 1.txt. So we type cp space name of the file space name of the new file that we're about to create, enter, and ll to check the result. And our new file 1.copy.txt is here, having the same content as the file it's been created from. We remember the tree command that shows us nested files and folders in a structured way. It's just convenient to use it to demonstrate copying files into the other directory. So let's copy all the files having names like new asterisk, where the asterisk is the alias symbol for any string. And we will copy them into the to directory. Checking the result with a tree command, and we can see all the copied files within the directory named to. We also might take a look at the to directory content and make sure all the files are there. Of course, we have a possibility to copy entire folders with all their content. So if we try doing it the same way we did it with the files, we will get the message telling us that for copying of the folders we need the -r key. So let's add it right in the end of the previous command. And it worked just fine now. The directory named to got copied into the directory named folder 2. We see it in the output of the tree command. For moving files, we use mv command. As an example, let's move all the files with txt extension into the directory named folder 1. Then check it with the tree command or ls command. So all those files are now located in the mentioned directory, but not in the current one, because we have moved them. We easily move a folder right the same way. So mv space the moving folder name space the destination folder name, check the result using any suitable command, and it's done. In Linux, there is no particular command for renaming files, because this operation is a form of moving. So we have to use the mv command for it. It works like this. mv, the current file name, the new file name, enter. And here it is, our new file got the new name. So if for copying files we use cp command, for moving and renaming mv command, then for removing we use rm command. To delete a file we simply type rm, target file name, and that's it. Check it out, no file. But when we tried doing the same for the folder, we got error message, cannot remove a directory. It's because the -r key is required to delete a folder. If we add this key, the folder will be gone. Now we are going to type this command, rm f *-r, which means that we want to delete all the folders whose names start with F symbol. And I've got a quick test question for you. Do you understand why this folder 1 is still here, not deleted, I mean? If you do, that means you get the Linux right. The answer is that the left directory name starts with uppercase F symbol, while we claimed to delete folders with names starting from lower f. Okay, now we will delete everything from the current folder. rm *-r. Check it out, nothing is here anymore. Let's take a look at rm help, the short manual for the command. There are a few keys that I would like to draw your attention to. I mean the R key and the F key. R means recursive deletion of directory and all its content. F means forced deletion, like no questions asked. So let's discuss rm command in this look. rm-r f and /. First, guess what this short line is gonna do. rm is for removing. -r key stands for recursive, nested files and folders. -f key means forcing, and / is the directory where we're going to start from our deletion. So this command would try to delete everything possible. I put the hash symbol in front of it so that it doesn't run but stays in history. By that example, I wanted to emphasize the idea that in Linux there are many ways to shoot yourself in the foot, so be careful. By the way, there is no trash can for the files deleted from the console. In this section, we discussed basic file operations, such as copying, moving, renaming, and removing. We will take a look at different text file viewers in Linux. But firstly, we will remove all the files from our Linux course directory because we don't need them anymore. So the command that we already know, rm *r, will do it for us. And the folder is empty. There is one more trick I want to do now. I'm going to run one magic command to download some long text file. It's not the command we're learning in this section, it's just a piece of software to help us download the file from the web. So we type wget space and URL for the required file. Downloading process might take some time, but when it finishes, we can see a new file in our folder. Its name is 1112.txt. We'd better rename it. And you have already known the command that will do it for us. It's mv. So mv, current name and the new name. Voila! The new name is Romeo poem.txt. Actually, it's the full text of Romeo and Juliet, poem by Shakespeare in this file. I took it just as an example of some long text file to demonstrate file viewer's functionality. And the first command we're going to learn in this video is more. By typing what is more, we can see one-line info on this command. Or more --help will show us some useful options. And of course you remember the way to call the most descriptive help info on command. It's man, more in our case. The Q key to exit to the console. So the simplest way to use our command is typing more and the name of the file we want to view. After pressing enter, we will see the first page of our file. Using the space button, we can bring on the next page to the screen. Using the Q button, we exit from the viewer to the command line. Let's discuss a few nice options we can use with more command. If we add dash and some number before the file name, then we will see only the certain amount of lines outputted for us. And it's 10 lines in our case. When we press space, then we will get 10 more lines of the file content. This is how this dash option works. The other option is plus sign and then some number, like plus 145, which will output the file content starting from the 145th line. So now we know that the prologue starts from this line. We can continue scrolling by pressing the space button as well. Q to exit. Of course, we can combine these options and use them together, like plus 145 minus 5, which will bring us to the 145th line of the file and show us only 5 lines from there. And the space button will show us 5 lines more per every press. Q to exit. In the short help for more command, there was an option starting from plus and slash, which allows us to search some text within the file. Let's check it out. We're going to add -5 option as well to output just 5 lines, no more. Then plus slash and string we'd like to search for. Let it be Romeo. Enter, and who would guess that there's no Romeo word in the most known Shakespeare book? Huh? And if you got the reason why we hadn't found it, then you're starting to understand Linux. So the problem was that we typed Romeo starting from the lower R, whilst Linux is strictly case sensitive. And we're going to prove that by fixing the R letter to uppercase in the search string. Check the new result. Now it's been found. Let's take a look at one more useful option for the more command. It is -s option. Now we will observe how it works. Look. In the mere output of more command, with no specific params, we can see that there are a lot of empty lines following together. And if we use -s option in the more command, then those doubled, tripled empty lines just have collapsed to one empty line. So this is the way we can use our screen more efficiently. The next file viewer we will discuss is less command. Its use is as simple as the previous one. So we can type less and the name of the file, the same way. And here we have the ability to scroll the text up and down with the arrows or with the page up, page down buttons. Exit from the viewer is also the same, the Q button. Let's discuss some interesting options of this command. Like for search, we use -p option. And then the text that is being searched should be placed within the quotes, like this. -p, quote, Romeo, quote, enter. The answer that nothing has been found means that we should either start our Romeo name from the capital R, or we can tell the less command that we don't want case-sensitive search. So if we fix the Romeo word, then we will see it emphasized in the file text as being found. When we want case-insensitive search, we do it by using -i option, and the I letter here should be uppercase, like this. And here we see that it found Romeo with only the first letter capitalized and the whole word written in uppercase letters as well, which itself is case-insensitive search. When scrolling the text down, we will see all the other search results emphasized for us. One more nice option of the less command is -n, capital N. This one gives us line numbers on the left. Could be handy for some cases. By the way, we can write these options separately, like this, -n, -i, -p. And it'll work absolutely the same way. So this is the less command, the text file viewer, that has more functionality than the previous more command. If we want just a brief look at some file, there is such an opportunity. It's head command, which allows us to output only a certain number of rows from the file. Default number is 10. So head and the name of the file will show us just 10 lines from the text file. And of course we can manage desired lines count using the -n option. For example, head -n1 Romeo poem.txt will output for us only the one line from the beginning of the poem. We can eliminate the n letter, leaving just dash and the number of lines with no change in the result, like this. Let's say we want 3 first lines or just 4 lines. There is -c option, which allows us to set the number of bytes we want to output, like -c 47 will show us the first 47 bytes or symbols of the file. And the last text file viewer we're about to discuss is the tail command. As you might have noticed, programmers like references, like less command is the reference to more command, as well as tail command is the reference to head command. It also helps us to remember all these commands. So, usage is simple and the same as the previous one. Tail, file name, enter. This will show us the last 10 lines of the file. And the short help for this command displays us info about how we can customize our result using different options. For example, if we add -3 option, this will obviously output for us only the last 3 lines of the file. -c option allows us to set the number of bytes that we want to see. The same as for the previous command, just for the end of the file. So in this section we were talking about text file viewers, such as more and less, head and tail. The first editor we're going to look at is Nano. The very short description of Nano says that its name is the reference to Pico, the other text editor, the previous. It's again about programmers love to references. Anyway, if we type nano and press enter, we launch this editor. Let's discuss its interface. The upper white line shows us info about the editor itself and its version in the left corner. In the midst of this line, there could be the name of the file in case the text is saved. The main part of the screen takes the editor itself, where we input our text. The white line below is the info string. Here can be shown the caret position, the size of the file, etc. The last two lines are devoted to main hotkeys for work in the editor. For example, caret x means exit from the editor to the command line. By the way, the caret symbol means control button here. So pressing Ctrl X means we want to exit, or Ctrl O is for saving text to the file. To undo some action, we have to press Alt U, because the M symbol in this help line means Alt button on the keyboard. Let's say we have inputted some text and want to exit. Then we press Ctrl O to save our text first. The editor will offer us to input the file name. Let it be like new file.txt. Enter, and our new file has been created. Then we press Ctrl X to exit from Nano to console, where we will see our new file. We can check its content, it's all good. We can open the existing file in Nano by typing nano and file name. Then we continue editing, make some changes, press Ctrl O to save and Ctrl X to exit. So new changes are here. There is one more interesting feature that Nano offers us by using -B option. Please note that the B letter is capital. Look at how it works. So we open a file with this option, edit it in some way. Let's just delete several lines of the text here by pressing Ctrl K, then save the file. And what we see in our folder, look. There are two files having our name, and one of them has a tilde sign in the end. Let's have a look at these files' content. So the first 10 lines of the original file says that it is our file as we saved it. And the other file with the tilde looks like we never edited it, which means that the last file with the tilde is the backup file created after we started editing the original file. So -B option in Nano Editor creates a backup copy of the original file. Isn't it neat, huh? Also, we can open a file using some numbers, like this, plus 3500, 20, and the file name. What this will do for us is it'll open the file and place the cursor on 3500 line and the 20th symbol. It can be useful when we finish editing a file and then the next day we want to continue it right from the line we left it before. The hotkey that shows us the info line in the bottom is Ctrl C. Here we can check the line we are at and the number of the column as well. The important part here is that we cannot put spaces here when using this option with plus sign and numbers. This way it won't work. See the error message in the bottom of the screen, double Ctrl X to exit. Let's take a look at the editing capabilities of Nano. For example, it can work with the clipboard quite conveniently. Let's say we want to exchange the first two lines of the text, for the author to be in the first line and for the title to be in the next. So we put the cursor in the first line and then press Ctrl K to cut the text from the line. Then we move the cursor to the next line after the author and press Ctrl U to insert text from the clipboard. Now let's play with text copying. So first we have to highlight the required text. We put the cursor to the needed position, then press Ctrl 6 to start highlighting. Then we move the cursor to the end of the block we are about to copy and press Alt 6 to copy. Move the cursor to the new position where we want to insert our text and press Ctrl U. And here it is, our duplicated text. Nano Editor can do search and even search with replace. After pressing Ctrl W, it offers us to input a search string. Let it be Juliet. Then we press Enter and it shows us the first occurrence. To go to the next occurrence, we ought to press Alt W. And we can go further and further through search results by using this keystroke. We'll go back to the beginning of the file and observe search with replace feature. So to call it, we press Ctrl/. And down in the info panel, Nano offers us to enter a search string. Let's input Romeo and Juliet. After pressing Enter, it will offer us to input the replacing string. Let it be boy and girl. Enter, and it shows us the first occurrence to replace. Look at what options Nano offers us now. They're shown in the bottom left corner. The Y does replacement for the current highlighted text. The N key means no. A key stands for replacement for all occurrences. And Ctrl+C is to cancel the whole operation. So we press Y, Nano replaces one string and it highlights the next search string to be replaced. We press Y again, and the next occurrence, let's press A to replace all other Romeo and Juliet strings in the file at once. We can now see the new strings, boy and girl, everywhere within the text instead of the original name of the poem. Okay, next feature. As long as our file is quite huge, we might need some functionality for cursor navigation. And we have it. So after pressing Ctrl, Shift and minus, the editor will offer us to enter the line number we would like to go to. Let it be 300, for example. Enter, and we see our cursor on the line we wanted. To make sure, we can press Ctrl+C to show the line info string down in the bottom. And of course, the line number is 300 there. And the last feature we will discuss about Nano now is the undo capability. To call it, we simply press Alt-U as many times as we need it. So finally we got back to the file content that we had when we just opened the file. In the end, I will just exit the Nano editor and I won't tell you the keyboard shortcut to do this, as I hope you have remembered it, or at least you know where the hint is shown. The next editor we are going to discuss is Vim. What is so special about it is that it is the default Linux text editor, which means that it is installed there right out of the box in most Linux distributions. So it's the editor you will most likely work in Linux. One more specific thing about it is that it looks and works not really intuitively, not obviously compared to all contemporary text editors we're used to. But the fact that it is the default Linux editor makes it very important. So that is why every person learning Linux should know at least its basic usage. One line help says that Vim is VI improved editor. So VI editor is its predecessor, although Vim substituted VI almost in every distribution. I mean, even if we input VI in the command line, most likely it'll run the Vim editor, not VI. So the simplest usage is this. We type VI and the file name we want to open. And the first thing we will learn about Vim editor is exiting from it, because it's a really tricky task if you don't know it. There's even a joke that some programmers reboot the server to exit from Vim. I wouldn't also call this editor a user-friendly one. But anyway, to exit Vim, we type : and Q, where Q stands for quit, as you might have already guessed. Okay, great. First task has been learned. But we open text files not just for exiting from them. Sometimes we want to edit them. So we open the file again, and our attempts to write some text lead to nothing in the good scenario. So what's wrong? And here we have to learn the Vim modes. The idea is that the editor has several modes of work. Let's talk them over using this schema. On opening Vim, we enter normal mode, It's like some lobby, a starting point where we decide what we want to do. So we press I button, which stands for insert, and enter by it the insert mode. In this mode we can edit text. To get back to normal mode, we press escape. If we want to use some commands, then we have to enter command mode by pressing colon. Now we can save changes to the file or quit from the editor or do some other command. To get back to normal mode, we press escape again. If we need a visual mode, we get there from normal mode by pressing V, which stands for visual. So this is how we switch between Vim modes, depending on what we are about to do. Okay, now when we know about Vim modes, let's check them out. By pressing I button, we enter insert mode. It's text editing itself. Then type some text, blah blah blah. To finish editing, we have to exit insert mode to the normal mode by pressing escape. And now we decide what to do next with our changes. So now we're going to save the changes we have made to the file. To do it, being in normal mode, we type :W, where W stands for write or save. Enter, and now we see the corresponding message that our file has been saved. By the way, we could have done it in some other way, like this. While we're in normal mode, we might type :WQ to write changes and quit from the editor. Enter, and we're back to the console. Let's say after some occasional editing, we want to discard our changes made to the file in Vim Editor. By the way, it's an important feature to remember first. I mean, exit the editor without saving changes. To do so, we press colon to enter command mode and then type Q and exclamation mark, where Q stands for quit and exclamation mark means like no questions asked. So this command will exit the Vim and make no changes to the file. If we open this file again, we can make sure that there are no changes. There are specific, interesting though, commands in Vim Editor. Let's discuss some of them. We can press DD to delete the line where the cursor is. And even more, if we type 5DD, this will delete 5 lines in a row. 2DW is to delete 2 words from the current position. P is for insertion from clipboard. U is undo, though 3U is undoing the last 3 operations. Let's move the cursor to some other position before talking over other commands. So, we can even move our cursor in a Vim specific way. For example, 2W relocates the cursor 2 words to the right. 10H moves it 10 symbols to the left. 3J moves it 3 lines below. 5K moves it 5 lines above. Of course, like every other respectable editor, Vim supports search. We use it in normal mode by pressing the / symbol. And then we type the string we want to search. Let it be Romeo. Press enter and our cursor is blinking at the first occurrence. To move to the next search result, we have to press N symbol and then N again to go further through search results. Moreover, Vim supports plugins. This means that it is possible to enable syntax highlighting for some programming languages. You can add Git support. It is system of so-called control version. Some people make kind of fully functional, relatively, IDE, which is an integrated development environment. I'm personally not one of those old school guys. I just know about such a possibility and prefer modern technology when I have a chance to use it. Why is Vim so important, regardless of its, let's say, not obvious interface? Because Linux runs billions of devices all over the world, starting from smart vacuum cleaners and up to Android phones. So there are many cases when you have to edit some config files without the possibility to install your beloved editor, while there always will be Vim by default. As some bonus trick, I want to introduce you to the Vim tutor. It's a simple tool to learn the most frequently used features of Vim. So, to use it, you simply type Vim tutor in the console and press enter. It might turn out to be that this tool is not installed on your Linux system, like here we have now. But it's not a huge problem. To fix it, we will run just two commands. The first is sudo apt install Vim. It'll install the extended package of Vim editor. Likely it'll ask us for the password, then we have to enter it. If it asks for our confirmation during the installation process, then we have to press Y to agree, like yes. And the other command we will run is sudo apt install vim-runtime. And we'd better add here -y key at the end of the line, so that the installer does not ask us anything. With the -y option, we kind of agree with any question in advance. So when the second command finishes its run and we have our command line free, then we can run Vim tutor again. What we see here is just a text file opened in Vim editor, and this text contains about 7 small lessons on Vim features. When I say small, I mean that its text won't be more than half of the screen or so. I highly recommend you to get through this educational text, at least briefly. It will help you a lot with Vim understanding in future. For example, it explains work with Vim starting from navigation, which is possible to do with H, J, K, L symbols. It teaches exiting from the editor as well, the colon, Q, exclamation mark command, which we discussed too, the basics of text editing, etc. I highly recommend you Vim tutor. To exit from it, we type :Q, obviously. By the way, after installing the extended package of Vim, it'll become a bit more user-friendly, which is quite reasonable for this editor. The last few words about Vim tutor. It can happen that Vim tutor will open its educational text in some other language. The reason is that it corresponds to Linux default language on your machine. So, if you want to change the language here, it is simple. After typing Vim tutor in the console, you just have to add the desired locale, like DE for German or ES for Spanish, EN for English, etc. This section was devoted to text editors, and specifically to Nana and Vim, and as a bonus, Vim tutor tool. If you check out the contents of the root file system using the ll or ls commands, you'll see the folders that are hanging out there. These are standard folders in various Linux distributions, and we're gonna talk about what they do right now. In the bin directory, you'll find executable files for the basic, most essential terminal commands in Linux. Some of these you might already know, and some we're gonna dive into later in this course. Feel free to scroll through the output of the lsbin command and spot any familiar commands. The boot directory holds files needed to boot up the operating system's kernel. The CD-ROM directory used to be the go-to for mounting CDs, but these days, for mounting any additional drives, whether it's USBs or hard drives, you typically use the media or mounted directory instead. The dev directory, short for devices, contains device files. So, for example, if we connect a printer to our Linux machine, it'll show up here as a file. The etc directory stores configuration files for services, system settings, and user programs. So, if we're developing any software for Linux, it's common to stash configuration files in the etc directory. The home directory, or /home, is where the home folders of our users are kept. So, Generally, the path to a user's home directory looks like /home/username. In our case, we see /home/itguy. This is the home directory for our main user, the one we're logged in as right now. The lib directory, which stands for library, also encompasses lib64 and lib32. These are library files that are essential for the operating system to function and boot up. In the lost and found directory, the operating system stores files that it managed to recover after a crash. So, if Linux goes down, you can check this directory to see if you can find any lost files. The media directory is the main mount point for extra disks. We'll chat more about this folder later on in this lesson. Sometimes the mnt directory is used for these purposes as well. The op directory is short for optional, which means it can hold additional files, add services, and so on. The prods directory contains files with information about running processes. And yes, prods is short for processes. Next up, the root directory is where the home directory for the root user is located. Since this is a completely unique user with a special set of permissions, their home directory is kept separate from those of the regular users. The run directory contains application state files, including Unix sockets. This bin directory, similar to bin, has binary files and utilities needed for configuring and administering the root user, aka the super user. The serv directory holds server files for services like FTP or the Apache web server and so on. Finally, the temp directory is like a shared folder where everyone tosses in whatever they need. So, think of it as the go-to place for user files. An important thing to note about this folder is that files in it don't get saved when you restart your system. The user directory, which stands for user, is where user programs are stored. So if we're developing software for Linux, we can stash our code here. And then there's the /wa directory. It holds temporary files, logs, journals, and other caches. You can also find these directories in the user interface if you open up the Explorer. Now, let's check out some commands that give us useful info about the file structure. Let's kick things off with the df command. A quick reference shows us the basic flags we can use with this command. But let's jump into some examples. Typing def without any extra flags gives us a pretty vague picture. So let's spice it out by adding the age flag. This means human readable, which changes the measurement units so we see gigabytes, megabytes, and kilobytes. Also, if we add the t flag, remember, case matters. This will give us a column showing the type of the file system. And there it is. So what does the df command display for us? It shows all the file systems on our machine. The line that catches our eye is the one ending with a slash and the mounted on column, meaning it's mounted at the root. And as we know, that slash is the root of the file system, which means this is our main disk. Let's filter the output to just keep that line by adding a slash at the end of our command. We'll ditch the extra info on the screen and keep only what we need right now. So, what do we see here? We see that our machine has allocated 15 gigabytes of disk space, with 8 of those being used and around 5 free, which makes up 64% of used space. But check out this interesting detail. If we add the iflag to this command, which stands for inodes, we find out that our used space is actually 21%. So, how much space do we really have free, and how much is used? Is it 60 full or 21? And here's where we need to talk about something called inodes. We'll go into this more thoroughly later in the course, but let's touch on it a bit now. In Linux, each disk has a specific quota for the number of files you can create. In this case, we can create about 900,000 files total. Out of those, we've already used 192,000, leaving us with 700,000 free. That accounts for the 21% of used space on the disk. So, in Linux, it's possible to run into a situation where you can't create a new file, not just because you've run out of megabytes, but also because you fit your file quota. So it can be beneficial to keep an eye on this parameter too. In megabytes, we've used 64% of the total space, but in this, we've used 21%. That's how you should read this info. Another helpful bit of info that dev can give us is the path to where we've mounted extra disk devices. Flash drives, CDs, external hard drives, and all that jazz. So, for example, let's pop in a disk with the guest additions. Now, let's run the df command again, and just like that, we see a new line pop up in the output. Turns out our guest additions disk is mounted in the folder mediate guy with the name of the disk. If we were to eject this disk, say by clicking it in the user interface, that line would disappear from the df command output. Check it out. All gone. No more info about the guest additions disk here. Next, let's check out a utility called do. Do stands for disk usage. A quick help command for this one tells us it allows you to check how much space is used on the disk. You can run it with different flags. For instance, do's will show us how much space our home directory is taking up. It's like a summary, giving us the total. It's also handy to add the H flag, which stands for human readable, so it shows the info in megabytes or gigabytes in a more understandable way. And look at that! Our user's home folder is around 16 megabytes right now. You can display all the contents of our folder, say with the command tree. We don't have much in this case really. Using do with the flags, HEC gives us the size of each file and folder. And there it is. At the end it totals everything up, showing the overall size. If you want a more compact output, try do HS, where S stands for summary. This way you get only one total line. You can also filter the output by specifying a file name, for example do text. So we want to see how much space the text files take up. But in this folder, there aren't any. Let's move to another folder where we do have a few texty files and run do again. Now it only shows those files and their sizes. We can also throw in some flags like HC for clarity and usefulness. C flag gives us a total line at the bottom with the sum of the contents. We can even exclude files matching a certain pattern from the search results. You do this with the exclude flag in this format. Put the pattern in double quotes and you'll see everything else, but our text files takes up 32 kilobytes. Clearly, that's the content in our folders. Speaking of file structures, let's consider concepts like archiving and compression. You'll also notice, in Linux, these are two different things. The default utility for working with archives is called tar. You can check out the help for using it. Let's look at the files we have and archive one of them. Let's choose the poem Romeo and Juliet. So, we tab tar, the flags C, which means create, so we're making an archive F, which means we're archiving a file. Then the name of the archive, the target file, a space, and the name of the file we're actually archiving. And from the outcome of our command, we see a shiny new file, display on a red background. That's our archive. We usually think an archive takes up less space than the original file. But if you take a closer look at these two files we have, you'll notice that the latest one we just created is actually a bit bigger than the original text file from which this archive was made. That's because we didn't use compression when we archived it. Let's run the same command that created our archive, but this time we will add the option. We'll change the file name a bit. Hit enter. And look, a new archive file just pops up. Now let's check out its size. Well, it's about 3 times smaller than the original file, because this time we used compression, unlike the last time. So in Linux, when you archive a file, you have the choice to compress it or not. Now, let's create a new folder and move our archives there. Here we go. We have a backup text folder with all our archives. Let's hop into it And now check out how to extract a file from the archive. For this, we use the tar command with the X option. X stands for extract, meaning we're going to pull something out. Let's extract the file from our archive. Let's see the result. Our poem Romeo and Juliet is now there as a text file. Here's another example. Let's say we have a file, just the text itself, and there's our archive. Remember, in Linux, a file doesn't necessarily need an extension, so we can definitely have a file like this too. If we want to see which files are packed in this archive, we can use the tar tool with the options to view. Just like this, and it's immediately clear that this archive contains 4 text files. If we want to extract files from this archive, we simply type tar with the options xf, add the archive's name, hit enter, and look at that! We can see the new files extracted from our archive. That was a tar utility. Besides tar, there's another tool for working with archives that you might be more familiar with, zip. Linux has a zip package. Let's quickly install it using the command sudo apt install zip. You know, the zip utility might be a bit more user-friendly because to create an archive, you just type zip, the target file name, and then list the files you want to add to the archive. Like for example, *.txt. Let's check it out, and voila, we've got our little red archive. Now let's move our archive to the folder 2, which is one level up. Let's jump into it. Let's double check that the zip file is really here. And now, to unzip our file, we just type unzip and the name of the zip file. Checking it, and everything is great. The file's been unzipped. If you're not a fan of memorizing options in the tar utility, you can definitely use the zip archiver, but you'll need to install it separately. So, in this section, we've talked about the folder structure at the root of the file system, the df and the tools for checking disk space, and we also touched on archiving and compression while looking at the relevant utilities. The command in Linux that is used for searching files by default is find. Let's remember what files we have in our current directory. Okay, 3 files. So the find command without any parameters shows us all the files in the current directory. Of course, we can type in the name of the file we are searching for. But look, if we type, for example, new_file, this cannot find anything for us, although we know that the file with such a name exists in this folder. So our error was that we haven't specified the file extension. And now we've made sure that it's a part of the file name. If we don't remember the file extension or don't want to specify it for some reason, then we may enter asterisk, which stands for any string, including an empty one. So from the last 2 examples, we see it. The find asterisk command will output for us all the files in the current directory, as well as find without any option. Guess what we will have in the output if we type find new asterisk. The important moment here is that the new word is typed in capital letters. And you have already known that Linux is strict to the letter case. So this command will show us 0 files in the result. But for such occasions when we don't know in what case the file name was written, we have this -iname option. It'll make the search independent of the letter case in the file names. Look at the result. The new file.txt was found this time. The asterisk symbol can also be used to substitute any file name when we know only the file extension, like this. Find *.txt. This means that we want all the files with txt extension, and we don't care about their names, as we see in the result. To demonstrate further capabilities of the find command, let's create some new files. Before I started typing the command to create a file, you can check yourself whether you remember it from the previous lectures or not. The touch command can help us with fast creation of several files at a time. Let their names be report 01, report 02, report 03. Check them with ls command, it's okay. So let's continue with our search experiments. Find report will show us nothing, as there is no file with this precise name. But there is a file named report01, and we can find it by directly typing its name to the end. To find all our reports, regardless of the number, we can use the asterisk, like this. Find report asterisk. So now we know about the asterisk symbol, that it is the alias for any string. But there is one more alias we can use here to substitute just one symbol, and it is a question mark. For example, if we type find report question mark, this will output for us all the files whose names start with the word report and have exactly 2 more symbols at the end of the name. If we change our command to find report and just one question mark, this will find us nothing, of course. For it to be more obvious, let's create some more conventional reports with 3 digits at the end of the file name. Okay, they're here. So now we will repeat our previous command with 2 question marks after the report word. And now in the results, we see only files with 2 digits at the end. If we add one more question mark, then the results will only be files with 3 digits at the end. So, to recap this aliases topic, the asterisk symbol can be used to substitute any string, including the empty one as well. While the question mark symbol means any, but only one symbol within the file name. Let's get back to find command itself. Until now, we used it to search for files in the current directory only. But we can specify the path where we want our files to be searched. For example, find tilde will output everything behind the tilde folder. What is the tilde concerning Linux path? We discussed it in the former topics. So tilde is the home directory of the current user. We have here outputted a huge bunch of files. But if we decide that we don't want to go too deep within subfolders during our search, we may use the -max depth option. We just add it at the end of the command string, like this. And now we've done the search exactly in our folder, without going into its subfolders, because the depth of the search is just 1, as we specified it in this example. So with this option, we can decide how deep we want to look in our search. One more option of the find command we will talk over is -size. This one allows us to define the exact size of the files we are looking for. Or it can be used as a definer of lower or upper margin of the file size. Let's say we want only files with a size of more than 10K. Then we use the -size option with the refinement plus 10K. This will show us only our Romeo and Juliet poem and its backup that we made. The K letter here stands for kilobytes, obviously. If we want to indicate megabytes, then we will use the upper M letter. If we are interested in all possible specifications for the file sizes, then we can find it within the user manual for the find command. We open its complete manual by typing man find. And here we're going to scroll down to all the possible size suffixes. Lower K is for kilobytes. Upper M is for megabytes, upper G is for gigabytes, etc. So it was the find command that we were observing in this section of our course, including its syntax, popular options, and some use cases. Let's chat about users, starting with how to pull up info about them. For instance, there's a command whoami. This one will show us the user's login name. Then there's the command groups. It gives us a list of the groups that the current user belongs to. The ID command will dish out even more info, like the login name, the UID, which is the user ID number, the primary group, and a list of additional groups along with their corresponding numbers. Let's switch to a different user. Say we have a user named salesguy on this machine. We use the su command, which is short for switch user. You just put the user's login name we want to switch to, hit enter. Then you enter the password. You probably noticed that the password doesn't show up as you type it. But don't worry, just type it in, hit enter, and now when we use the same commands, WAMI, groups, and ID, they'll give us info about the user sales guy. If you want to switch back to your previous user, IT guy, just type exit to return. Now, if you run the su command without specifying a username and instead use the prefix sudo, which stands for superuser_do, you can switch to root mode. So, when you type sudo su and hit enter, it'll ask you for a password, and this command kicks you into root mode. The command wami will now tell you that you're root, and the ID command will return matching info too. You might also notice that in root mode, the command prompt looks a bit different. Whether it's highlighted or not can vary from one machine to another. That last symbol, the hashtag, tells you that you're in super user mode. If you see a $sign at the end of the prompt, that means you're logged in as a regular user. Type exit to get back to your user IT guy. So why is being in root mode useful? Here's an example. Let's try running the command apt install zip. This command is supposed to install the zip package because apt is the package manager, install is the action to take, and zip is the package name. But when we try to run that command, it fails because we don't have the rights to do it. We're locked out because that's an admin level command only root can run, or we can run that command as root. So we start with the prefix sudo, like sudo apt install zip, hit enter, and now it works just fine. But check this out, if we switch to root mode and then try apt install zip without any prefix, it runs successfully. This is exactly why root mode is necessary. It might be tempting, right? I mean, the idea of always working as root sounds cool. But don't let seduce you because it's actually a security risk, and generally in Linux it's a no-no to always operate as root. And I'd say it's even a bit more than that. In Linux, there's this widely accepted practice. You work based on the minimal necessary permissions needed to accomplish your current tasks. Let me illustrate with a simple example. Imagine we're working on a project in a team. We get programmers, sysadmins, and other IT guys. So, as a programmer, I might approach an admin asking for access to a server. A good admin would probably ask me what exactly I want to do on that server. I might say something like, I need to fix the config file, check the logs, update the code, and so on. A good admin will grant me permission specifically for those tasks, because in Linux it's customary to work with only the minimum permissions needed for the job at hand. So, just because I need access to the server doesn't mean I should automatically get root access. That's why it's not a good idea to get carried away using the root user all the time in Linux. Although I have to mention this topic can stir up some debates, as there are always admins and sysadmins who say they've been using the root user for ages without any issues at all. But those kinds of discussions just reinforce the general rule that's widely accepted. Especially when you're just starting to get familiar with Linux, I'd absolutely advise against working as a root user all the time. Now let's check out the info about the current user. The commands that brought this info up for us. We'll also talk about what happens by default when creating a user in Linux. We're used to coming up with a username and then calling that user by that name. But for the operating system, what really matters is the user number. So when you create a new user, they're assigned a number called AUID, user identifier. This is a unique positive integer. Also by default, when a user is created, a group with the same name is automatically created. And this group becomes the primary or main group for our user. This group also has a number, another unique positive integer, known as the git group identifier. And the user is automatically added to this group. You can also add the user to additional groups. You can do this later or right when creating the user. But it's important to understand that the list of additional groups and the primary group are different things. Right now, we'll learn how to get information about the list of active users. There's a command called users. It shows the list of usernames of the users currently working on our machine. Then there's the w command, which displays this info in a more detailed table format, and also the who command. Right now, all three commands have shown us that we have just one active user, IT guy. Now let's perform a remote SSH connection to our server with a different user. Let's open the PuTTY program and get ready to connect. We'll type in the username, then @ and server IP address. Use port 22 and connect using the SSH protocol. Then we click on the open button. After that, we confirm the connection and type in the password, and boom, we're in the server. Now let's go back to the PuTTY terminal and run those same commands again, and guess what? We'll see there are already 2 logged in users, 2 active sessions. The IT guy user is joined by our new user, outgoing HR, on whose behalf we just logged in using PuTTY program. We can switch back to the main window of the virtual machine, run those commands again, users or w or who, and we'll notice that there's now info about that extra user as well. So basically, these commands give us the rundown of all the users connected to our machine. The main command for creating a user is userat. You can check out the help by either typing what is userat or userat --help. Let's dive into some parameters of this command. For instance, $g option lets you set the primary group for the user. Meanwhile, the G allows you to specify a list of additional groups. Remember, in Linux, letter case matters. So these lowercase and uppercase g's are totally different options. The small m option tells us that we're going to create a home directory for our user. And there's also the lower d useful option, which allows you to specify where that home directory will be located. Another one important is -p, short for password, which lets you set a password. But hold up, this actually means you can input the password hash here. It's better to steer clear of this option, because it saves hash password in your command history, which is not exactly safe. So it's much smarter to set the password later with a different command. Another key option is -s, which stands for shell. It allows you to specify what shell the user will be using. And you can even assign a user ID, so-called UID or UID, upon creation with the -u option. Let's create a few users using this command. So we type sudo userat, since this is an administrative command. We're running it as root, which is why we use the sudo prefix. So we use sudo userat, and then the username. Let's call this new user office manager. Press enter. Great, now let's create another user. We'll name her Smiley Girl. When creating her, we'll use the m option to indicate we want to create a home directory for her, just like we saw in the help guide. For the next user, let's mix in some more options with the userat command. We know that -m option means we'll be creating a home directory. Then the d option lets you specify the home directory address. Let's say it's /home/theboss, even though the user's name is Big Boss. We'll also add the s option, which is for the shell, and we'll set it to /bin/bash. That's the most popular shell in Linux. We'll dive into that more in our course. After we've created all these users, let's check out the content of the home directory. We type ls/home, and we see directories for IT guy, Smiley Girl, the boss, and sales guy. These are the home directories for our users. But Office Manager is missing because we created that user without the m option, so no home directory was made for them. Also, with the user_add command, you can check out the default options that will apply if you don't specify anything else. You can view these defaults with the upper D option. This option was mentioned in the help, and D stands for defaults. Besides user_add, there is also the add_user command. It also lets you create a user, but works a bit differently. Let's go through an example. We'll create a user like this, sudo add_user, and we will call him outgoing HR. An outgoing and friendly HR buddy we will have. So check this out. When we create a new user now, they ask us to fill out a bunch of fields right away, like coming up with a password, setting a name, phone number, room number, and more. At the end, they ask us to confirm the info. We can hit Y or just not press anything at all. Either way, the user gets created anyway. When we hit enter, that user is all set. We can take a peek inside the directory and see that this new user's home folder showed up, even though we didn't specifically say we wanted it. Let's check the command history to make sure that add_user command is there. But those values we entered, like the password and the name, don't stick around in the command history. So yeah, in terms of security, everything's good to go. Now we're gonna discuss what is the difference between the add_user and user_add commands. Let's see where they are located. Where is user_add and where is add_user? It shows us the path to the file that actually runs when we use the command. If we use the cat command to show the contents of /usr/sbin/add_user, we can see it's a script. In this case, it's a Perl script. This means it's written in Perl and actually calls the original command, which is user_add, beneath the surface. Now, if we look at the contents of /usr/sbin/user_add, we realize it's a binary file. There's no way to display that in text form, it just doesn't show up correctly. So to wrap it up, the main command for creating users in Linux is user_add. It's found in all distributions. Add_user is just a wrapper script that calls the original command, and it might not be present in every distribution, so keep that in mind. If we try to log in as these new users, we'll be asked for a password each time. But what's the password for Smiley Girl? What about Big Boss? They don't have a password. So no matter what we enter, it's gonna be wrong. So as of now, we can't log in as these users. But if we try to log in as outgoing HR, it asks for a password, which we know because we set it up when creating the user. So we enter it and that user logs in just fine. We can check by typing, who am I? It shows us the username. Let's bounce back to the exit command. So, long story short, for the company's people or just these users to start working, we need to give them a password. In this case, we can do that with the passwd command. If we type what is passwd, it will give us info about the command. Since it's an admin command, we call it with a sudo prefix, meaning we're doing it as root. If we input sudo passwd and hit enter, we will change the password for the current user. But if we type passwd followed by a username, we will change the password for that specific user. Let's set passwords for the Smiley Girl and Big Boss users. We'll do the same for Office Manager too. So basically, this command is asking you to enter a password and then confirm it, just to make sure we didn't mess it up. Awesome, the passwords for our users are set and they can get started. Let's try to log in. We'll check and ensure everything's good to go. Smiley Girl can log in. Big Boss can log in, everything's working. In the command history, you can see that the passwd command was used. But of course, it doesn't save the actual passwords we typed in. And by the way, check out what home directory was created for Big Boss. It is /home/the_boss, as we set it when creating the user. In Linux, most services store all their settings in simple text files. And just like that, user lists are stored in plain text files too. Let's take a peek at them now. For example, we can use the cat command to show the contents of the file /etc/password. Here we can see all the users we just created, including root too. Every account on our machine is stored in this file. The format is such that each line shows info about a specific user. Let's break down what we see here. Every line starts with a username, then it's separated by colons into these columns. After the first column, there's an X everywhere. That X isn't just random. There used to be a password hash there. But later on, it was decided that it's not super safe to keep the password hashes in plain text files. So they moved it to a separate file. To keep things compatible and not break anything, they left the X here. It doesn't take up much space, and it saves programmers some work. The third column is the UID, or user identifier, which is a unique number for the user. Then the fourth column is the GID, or group identifier, which is the number for the user's main group. There might be some extra info about the user afterward. Following that is the home directory for the user, and then the shell. Sometimes it's /bin/bash, and other times it's /bin/sh. We'll talk about shells a bit later in this course. Next to some users at the end of the line, you can see either no login or /bin/false. That means we're looking at what you'd call daemons. In Linux there are three types of users. First there's root, the only one of its kind, with a UID of 0 and a GID of 0. Then the second category is the daemons. They're basically system accounts used to run processes or services. But these accounts cannot log in because they don't have a shell. They're for running services only. For instance, the SSHD account is a daemon account that runs the SSH service. By the way, daemon numbers are usually counted from 1 to 499, while human account numbers start from 1000 and up. Now, let's take a look at the next style, which is /etc/group. Here we see a similar format, and it looks like we can even spot our users' names. But let's not forget that this file has the names of user groups. We remember that when a user is created, a group with the same name is automatically made, so these names are actually groups. The next file with user information is shadow, and it's in the same etc. folder. If we try to open it, we'll be told that we don't have permission. Access denied. That's because this file contains sensitive information, which is only visible to the root user. So if we want to dive in, we need to announce our root rights, the superuser privileges, using the prefix sudo. With sudo we open this file, and now it shows up for us without any issues. Here, again, a similar format is used to store user data, but the information is a bit different. The main thing we're interested in this file is the password hash. After you log in, that long cryptic string, like abracadabra, is actually the password hash. Because serious services and projects never store passwords in plain text. They keep them as encrypted strings, just like that. We won't get into the nitty-gritty of cryptography and encryption right now. Let's just stick to this statement. To change an existing user in one way or another, we have the command usermod. As usual, you can check the help by either typing what is usermod or usermod --help. Here's a cool tidbit. If you look at the help for the usermod command by typing usermod --help and compare it with the help for the useradd command by typing useradd --help, you'll notice that they have pretty much the same options. In reality, both of these commands, usermod and useradd, work with a similar set of parameters. So let's say we have a user and they come with a certain set of parameters. We can set these parameters when creating a user with useradd, or change them later for an existing user using usermod command. Let's go through a few examples of how to use the usermod command. Imagine we want to block our user. Right now, for example, the user outgoing, HR can log in and work just fine. Everything's cool with their account. But let's say we need to block them. We can check the help to see what option we need to use for that. it shows us the option -L, which is short for lock. So we could type sudo usermod -L username. Since this is an administrative command, it's likely that we'll be prompted to enter password. Hit enter. After blocking, the user might try to log in again, maybe not knowing about the block. They enter their password and bam, they get an authentication error. They might think they typed their password wrong and try entering it again more carefully. But nope, they still can't log in because they're blocked. The thing is, the user isn't informed that they've been blocked. So for them, it feels like they just messed up entering their password. I also wanted to show you how elegantly and simply this mechanism works. If we check the familiar file /etc/shadow, we know that it shows password hashes next to the logins. And sure enough, our user outgoing HR has a password hash. Now, here's the crucial detail. This hash starts with an exclamation mark. That exclamation mark wasn't there before. It appears when we use usermod with the -L option. So, locking a user simply adds a single exclamation mark to the password hash. This messes up the login mechanism. Because the user types in the correct password, the correct hash is generated from that password, and it's compared to the hash stored here. These two strings will differ by just one character, the exclamation mark. However, for the system, those are two different strings. So, the operating system thinks the user entered the wrong password since the hashes don't match. And that's how straightforward it is. Now, to unlock the user, we just run usermod with the -U option. The U stands for unlock. Sudo usermod -U username, enter, and the user is unlocked. Before we check if the user is unlocked, let's take a quick peek at the /etc/shadow file to see if the exclamation mark in the password hash is gone. After that, we'll try to log in, and we can see that everything's working just great now. To manage users, we use specialized commands. But technically, you could also create and edit users directly by messing with the related files, etc. path_d, etc. group, and shadow file. This is called direct user editing. But honestly, I wouldn't recommend going down that road, because one little mistake could really mess things up. After all, when you run a command, there are some internal checks that prevent those really obvious errors from slipping through. But if we accidentally mess up the file format while editing, it could completely derail all user management in Linux. Let's play around a bit more with the usermod command. It can also help us change a user's home directory or set a home directory for them. Let's remember that the Office Manager user doesn't currently have a home directory. So, let's specify one and create it. We can do that with the usermod command using the -D option. After -D, we enter the path to the home directory we want to set, then the username, hit enter. Now we can check the contents of the /home directory to make sure no new folder appeared. But if we take a look at the contents of the etc/pass.wd file, we'll see that Office Manager now has a designated home directory, but we still need to create the actual folder manually. I think you remember which command will help us do that. It's make directory, or mkdir. Let's run it. We get the message saying access is denied, because only the root user can create directories inside the home folder at the root of the file system. So, to run the command, we'll need to add the sudo prefix at the beginning. Let's repeat it in that format. Check it out. And now, the user has a home directory. It's set, and the folder is present. Another handy feature of the usermod command is changing or setting the shell, because the shell determines the commands our user can use moving forward. Let's change the shell for Office Manager and Smiley Girl from bin/sh to bin/bash. That would be the command sudo usermod -s, which means shell. Then we specify the new shell we want, /bin/bash, writing the path to that file, the username, and hit enter. Let's do the same for the second user. Checking back in the path.wd file, and we see that our users now have a new shell. Task completed. You notice that the user we're working with IT guy can run commands with the sudo prefix, which means he's executing them as root or the super user. So if we try to run some random commands as another user right now, it won't work out at all. Let's check this out. We're gonna log in as the user smiley girl, input our password, and try to run a command that requires elevated privileges. Let's get our hands dirty with sudo apt install zip, which is just installing the zip package using the apt tool. It's pretty clear that this command needs root rights since it starts with sudo. Otherwise, it's not gonna run. This command is gonna ask us for a password, and when we type it in, it will deny us the right to execute it. Clearly, smiley girl doesn't have root rights. Now, let's get back to our IT guy and figure this out. What actually gives a user root privileges? Let's take a look at the group list for both IT guy and smiley girl. If you type the groups command without specifying a username, it'll show you the groups of the current user. But if you specify a different user with the groups command, you'll see the groups for that user instead. And here we see that smiley girl only has one primary group with her name. Meanwhile, IT guy has a whole bunch of groups. So, it's actually the membership in one of those groups that grants him root rights. And that magical group is called sudo. This means that if we add any random user to the sudo group, they'll get root privileges too. Let's prove it. To manage groups, add a user to a group or move a user from a group, we need to use the right options with the usermod command. If we forgot what those options are, we can always check the help. Typing usermod -- help will show us that we have the option G, which lets us specify a list of additional groups for a user. And we shouldn't forget about the A option, which means band, so we can add additional groups without removing existing ones. Alright, let's print out the list of groups for smiley girl one more time and add her to the sudo group. We can do this with the command sudo usermod -a -G group sudo smiley girl. Then hit enter. It might just ask for the password again. Let's check the group list for smiley girl again. And voila, now she's in the sudo group. Awesome. Now, let's see if she can actually run commands as root. Let's log in as her again. We'll try running sudo apt install zip. And look at that. It works like a charm now. So, being a member of the sudo group really does give a user root rights. If we want to take those root rights away, we just have to remove the user from that group. We can do so with the command del user. So, if we type sudo del user smiley girl sudo, we'll be taking smiley girl out of the sudo group. In this command, sudo at the beginning means we're executing del user as the root user, and sudo at the end is just the group from which we're kicking out the user smiley girl. Let's check out their groups again. Awesome! We've taken away their root privileges. Now, let's dig into why the sudo group is such a big deal. Do you remember when we tried to run sudo apt install zip but didn't have enough permissions? That line there tells us we're missing out because the user isn't in the sudoers file. So that means there's this file where all that info is stored, and guess what? It can also be edited. Let's take a peek at this file. You can find it at /etc/sudoers, but make sure you open it as root with that sudo prefix, otherwise it won't let you in. Any lines starting with a hashtag are just comments and not what we're interested in right now. Let's scroll down to the line that starts with root. And right next to it, we see the permissions granted to that user. You'll notice all is repeated 4 times, meaning the root user has every permission possible. They've got all the power. A bit lower, we spot another line with %admin, which has almost the same rights. Then there's %sudo, and it shows the same permissions as root. The syntax here is that if a line starts with a username, we can define permissions for that specific user right next to it. If it starts with a %sign followed by a group name, we're defining permissions for all users in that group. That's why %sudo gives the permissions for users in the sudo group. Now, let's break down what these notations mean. The first all is about the hostname from where the user is allowed to run commands. Then, there's all again in parentheses, which is the username allowed to execute commands. After the colon, you get the group name, and the last all lets you specify a list of commands accessible to that user. So those are the tools available in this file. Apart from the root user, it's super important to be careful when managing this file because changes happen instantly after saving. You could easily lose your root privileges. As we know, there are countless ways to shoot yourself in the foot in Linux. Before wrapping up the talk about users, let's tackle how to delete a user. We have the userdel command for that. You can check the help for it. And check this out. There's this handy -r key for removing, which means deleting the home directory and mailbox, if there's one, along with the user. Let's see how that works. Let's look into the /home directory. Remember, we have home folders for our users. Now let's delete a couple of users. We'll start with Smiley Girl. Now let's get rid of Big Boss. Oh wait, his actual name is not D-Boss, or rather Big Boss, while his home directory is named D-Boss. And that's the story behind it. We're gonna get rid of him with a -r trick, which also deletes his home directory. Let's check out the results. And just like that, we see that the boss's directory, which used to be the home folder for our user Big Boss, is gone. Meanwhile, the home directory for Smiley Girl is still hanging around. See, there are all sorts of ways to remove users. After we delete users, of course, all their info disappears from the files past WD, group, and shadow. There is no mention of them left here. In this section, we talked about working with users. Specifically, we went over how to display user info, create new users, modify users, delete users, and manage root privileges. To create groups, the main command you'll be using is group add. Just like always, you can check out the help either with the --help key or the what is command. Besides group add, there's also another command called add group. So, just like with creating users, you have your main command and then there's a wrapper script. In this case, group add is the core command that's found in all Linux distributions, while add group might not be available in every single one. Let's take a look at how to use these. Let's create a group called remote workers. They're the remote team, you know? You type sudo group add group name, and then, if prompted, enter your password. Now, let's check out the file etc group to see if our new group is listed there. The tail command is enough for us to check the last 10 entries. And there it is, our new group, remote workers, with a gate of 1006. But wait, no one's in the group yet. We need to add some users to it. We already know how to do that. We can use the usermod command with the -a and -g options. -a means to append additional groups, and -g, uppercase G, is for managing secondary groups. The syntax goes like this. Usermod -a, -g group name, in this case, remote workers, and then the username of the person we're adding. Oh, we can't add Smiley Girl because we already removed that user. Let's add someone else instead. How about sales guy? We'll also throw an outgoing HR and IT guy. After adding users to the group, let's peek back at the etc group file. And we can see that the usernames are now added to the line for the group. You can also use the groups command and type in a username to see a list of their groups and confirm that remote workers is now part of those users. When you want to delete a group, you use the groupdel command. You already know how to check the help for this. Using the command is pretty straightforward. Just type sudo groupdel group name. And that's it. The group is gone from the machine. You won't find it in the etc group file. And of course, it won't show in the list of groups for our users. You can check and be sure. It's all true. In this brief section, we covered how to create groups, add users to groups, and delete groups. If you use the ll or ls-l command to view the contents of a directory, you'll see everything laid out like a nice table, and the last column is where the names of our files and folders chill. Let's chat about the other columns now. The first column is made up of 10 characters and shows the permissions for the files and folders. The second column gives a number of hard links pointing to the file. We'll dive into hard links a bit later. The third column shows the file owner's name. The fourth column is the name of the group that the owner belongs to. Next, you'll see the file size, the date, and only then the name. Now, let's take a closer look at that first column. It's made up of 10 characters. The first of those 10 tells us the type of file. For instance, the letter D means it's a directory, because, yes, directories are a type of file too. A dash means it's a regular file. There could be other signs too. For example, an L indicates a link, aka a soft link. After that, we have 3 sets of letters, RWX. This repeats 3 times. Why 3 times, you ask? Because the first RWX tells us the owner's permissions. The second RWX is for the group's permissions. And the third RWX is for all the other users. If there's a dash instead of a letter, that means that particular permission is missing. As you might guess, the letters RWX stand for read, write, and execute. So, these permissions can be set separately for different user groups regarding this file. Separately for the owner, separately for the group, and separately for everyone else. Let's check out the permissions given to our file Romeo and Juliet by default. In the owner's permission set, we see our W-, which means the owner can read and write, but can't execute. The group of owners has the same permissions as our W-, while everyone else only gets our --. Here's a curious thing. We are currently in our user's home directory, and it turns out that by default, anyone else on this machine can read the files in my home directory. That's not how it works in Windows, so keep that in mind. So what do these permissions really mean? The letter R stands for read, which gives you the ability to open a file and see what's inside. When it comes to a directory, read permission means you can enter the directory and check out its attributes. W stands for write, so this permission allows you to edit a file. For a directory, it's about the ability to change the content inside, like adding a new file. Lastly, X stands for execute. This one's all about running programs, scripts, or binaries. For a directory, having the X permission lets you enter the directory and check its attributes. The tool that helps us change these permissions is called chmod, which stands for change mode. Basically, it lets you switch up how a file operates. In the command reference, they've laid out its syntax with different options you can use. You can go for letter designations or digit designations. Let's break it down step by step. If we're using letter designations, we start with a letter U, G, O, or A. The letter U stands for user, meaning the owner. G represents group, referring to a group of users. O stands for others, or everyone else. Letter A means all, so it covers absolutely everyone. So, basically, with these letters, you're picking a user category to change their permissions. Next, you'll use a plus, minus, or equal sign. A minus means you're taking away permissions. A plus means you're adding permissions. An equal sign means you're overwriting the access rights. Then, in most cases, you'll use the letters R, W, X to talk about additional bits, but we'll chat about that a bit later. That's the first version of this command syntax. The second version lets you use 3 digits from 0 to 7 to modify access permissions, and we'll show an example of that too. Before we dive into examples of how the chmod command works, let's clear out our directory. The ** command will delete all files, but it won't mess with the folders. Remember, to delete folders, you need to run the arm command with the -r option, which stands for recursive deletion. Let's create a new file and call it important file. It's going to contain some important info for us. We'll display some info about it and switch up its permissions. With the change mode command, we'll say we want to give others the O category, write permission for that file. We execute the command, check the result, and see that W letter has popped up in the permissions set for all others, just like we wanted. Here's another example. Using change mode, we're going to take away reading and writing rights from the group and others for our file. We check the result and see that a bunch of minus signs showed up. So we've taken away reading and writing rights for the group, and we took away reading and writing rights for everyone else with the same command. There's another way to use the syntax. Change mode G plus W, O plus R, for which file, for the wildcard symbol, meaning all files in this folder. Let's check the result. And look at that. The group now has W in their permission set, giving them write access. Others now have R, which is read permission. Now, let's check an example using the equal sign. With change mode, we're giving the owner all the rights to read, write and execute, comma. We'll give the group reading and writing rights, comma. The others will get rights just to read. For which files? For any file starting with the letter I, for example. We have one such file. We check the result and see that everything is just as we wanted. So, the owner has rights to read, write, and execute. The group has the rights to read and write but no execute rights. And for everyone else, it's just a reading access. Let's throw in another example where we set the same permissions for all user categories with one command. Change mode A equals RW. Here A means all, so we're giving everyone read and write permissions and taking away everything else. We're checking the results and see that our W dash shows up 3 times. Another way to set or change access permissions is by using numbers. So after the command to change mode, we can generally write 3 digits, each ranging from 0 to 7, which will define the permissions. The first digit from 0 to 7 sets the permissions for the owner. The second one does the same for the group of owners. And the third digit sets the permissions for everyone else. For example, we have change mode 640 for our important file. This means we've set permissions of 6 for the owners, 4 for the group, and 0 for everyone else. Now let's figure out what each number means. To really get a grasp on assigning permissions using numbers, let's take a brief look at number systems. So, on your screen, there's a picture showing all possible combinations of the letters R, W, X, or the dashes in the first column. If we replace the dash with a 0 and the letters with 1s, we get what's shown in the second column. We know that computers only deal with 0s and 1s, right? When we convert to binary form, we get those values. Then, if we convert those values from the second column to our familiar decimal system, we end up with numbers from 0 to 7. Why are we talking about this? Because the digits we can use for setting access permissions are decimal. So, 6 means 110 in binary, which corresponds to the permissions R, W, and dash. That's reading, writing but not executing. And a 4 will be 100 in binary, meaning R minus minus. So just read permission. And a 0 in any number system is always 0, meaning no permissions at all. Now let's discuss changing access rights for a folder. But first, let's create a couple of extra files and change permissions for the folder. Using the command change mode, let's go with the numeric option, say 764 for the dot. The dot represents the current folder. 2 dots mean the parent folder. So, we're looking at the current folder. Let's check the outcome and see that this specific set of permissions has been applied to the folder. These changes haven't affected the files inside the folder though. If when applying new permissions to the folder, we want these permissions to also apply to the files inside, we need to remember the key R, which stands for recursive permission changes. There's some info about this key in the help section too. Let's try running the previous command with it and see that our permissions now apply to both the folder itself and all the files inside it. So the letter R indicates recursive application of permissions to the object itself and to all the nested objects and files within it. Next, let's chat about the tools we have in the terminal for changing the owner and group of files. So, This is basically what we see in the third and fourth columns of the ll command. We're talking about the chown command, which stands for change owner. Pretty self-explanatory, right? You can peek into its help by using the command with the -- help flag, like you usually do. This command lets us switch either just the owner, just the group, or both at the same time with one command. Let's dive into some examples. And before we go further, let's highlight a key difference between the change owner command and the change mode command. The biggie here is that change owner is an admin task, meaning we need to run it as root, using the sudo prefix. So we'll type sudo chown, followed by the username we want to assign as the owner, and then the name of the file we're working on. Let's check out the results. Now we see that the owner of the file, another file, is outgoing hr. That's our user right there. Next, let's see how to change the group. The syntax will be like this: sudo chown : group name file name. Hitting enter now. Oops! This command throws an error because, as we discussed in the last lesson, we deleted the remote workers group. So, let's recreate that group, add a few users back to it, and then check the outcome. Let's make sure of that. Yet, indeed, the etc. group file is showing us that the remote workers group is no longer on our machine. Let's create this group again with the group add command. And let's peek at the etc. group file once more. Great, the group has reappeared. Now we need to add some users to this group. We can do that with the user mob command using the -a and -g flags. We've done this before, so it's familiar territory. Let's check the results again and see that now in the groups line, we've got the users we just added. That's IT guy and outgoing HR. Now, let's scroll back to the command we used to change the file's owner group to remote workers. Time to execute it again. Let's check what we got. Now, the owner group of the file important file is showing as remote workers. Also, this change owner command lets us change both the owner and the group at the same time. The syntax for that would be sudo chown, username, group name, file name. Let's see the results now. The user is sales guy, and the group is remote workers for the file one more file. As an extra example, let's change the owner group for all files in this folder to the group IT guy. Sudo change owner, : group name IT guy and asterisk. The asterisk, as we know, means all files in the current directory. Let's check it out. Looks good. Oh, and we can also use the change owner command on directories. For instance, sudo chown outgoing hr : remote workers period will change the owner and group for the current folder. Let's check that one out as well. But wait, we see a message saying access is denied. What's going on here? Essentially, we just switched the owner and group in the current folder to someone else, which means, well, now we don't have access anymore. Now we can't even peek at the contents of this folder. But, of course, that never applies to root. And since the user IT guy has root privileges, we can check out the contents of this folder with the sudo prefix, and it turns out our command actually worked just fine. This example shows that in Linux we can take away some permissions from ourselves, and then who knows if we'll be able to get them back. So we need to be careful. Let's give our folder all the permissions, 3 sevens, like 3 X's, so we don't run into trouble looking at what's inside this folder. Let's take another look at the command. The last command was change owner. Sudo change owner, username group name. In other words, we made these changes to the current folder. And as you can see, these changes didn't impact the files inside the folder. Everything works just like with the previous commands. So if we add the R option, which means recursive change, we can change the owner, not just for the folder itself, but for all the files inside it too. The documentation mentions this, of course, and we'll look at an example. So basically, we'll add the R option to the previous command. There's also another command in the terminal that lets us change the group of owners. That's chgrp, short for change group. We already know how to call the help command. Either use --help or the whatis command. Let's check out a couple of examples. We'll create a new file named some doc, and then we'll change the group ownership of that file using the chgrp command. So we type sudo change group and group name, then the file name, and we can check the result. It worked. This command is also administrative, so we use the sudo prefix with it. Let's also create a group called office workers. We can do that with the group_add command, which we've already learned about. Let's check the contents of the etc.group file. The group has appeared. Now let's change the group ownership of the current folder to office workers. The command will look like this: sudo chgrp office workers, period. The changes only affected the current folder. If we want to change the group ownership for all the files inside this folder, then, as usual, we use the -r option. Let's give it a shot. Add -r to the last command and check it out. Everything's great. It worked like a charm. Before we dive into talking about special beats, let's clear out our folder using the command rm with the r option and an asterisk. Got it? Now let's whip up a couple of new files. We'll name one public executable file and the other one can be private executable file. Awesome. Next, we want to give the public executable file execution rights just for the owner. You can hit pause on the video for a second and quiz yourself on what command with which options does that. Alright, it's the command chmod u+x to give just the user the right to execute, followed by the file name. Let's check it out. Great. Now the right set for the owner of this file has an X, which means the file's owner, aka tguy, can run this file now. Now let's chat about special bits. Let's kick things off with the suit bit. It stands for set user ID. We'll set this bit on both files. You can do this with the command chmod u+s for the asterisk, meaning for all the files in our folder. Let's see the result. We can see that the files are showing up on a red background, which is meant to grab attention. Also, there is an S sign now in the rights column. But if you take a closer look, one file has a capital S and the other has a lowercase s. What's the deal? The lowercase s is next to the public executable file, which we gave execution rights to for the owner. So, the small s means there's an execution right underneath it, and the big S as a raised suit bit means there's no execution right under it. Now, what happens if someone tries to run these files? Because the suit bit is relevant for executable files, some random user tries to execute the public executable file. The operating system will notice that the suit bit is raised on this file and will run it not under the user's name but under the owner's name. And the owner has execution rights. So any user can run the public executable file. The same kind of thing happens if someone tries to launch the private executable file. So some random user goes for it. The operating system sees that the private executable file has its suit bit set. This means it's running with the owner's rights. But since the owner doesn't have executing rights, no one will be able to run this private executable file. To remove the suit bit, we run the command chmod u-s for the specified files. Let's check the result, and we see that the s is gone. Meanwhile, x, the execution right, stays where it was. Where there wasn't an X, it didn't magically pop up. So the suit bit doesn't mess with access rights. It just changes how access rights are checked when trying to execute a file, because it's specifically about executable files and binaries. Also, keep in mind that the suit bit doesn't work for scripts in Bash. Next, let's chat about the skid bit set group ID upon execution. It's kind of like a similar bit, but this one relates to the group of owners. First, we're gonna change the permissions on our public executable file so that the group can execute it. You can do this with the command chmod 674 Basically, we want the group to have the highest privileges: read, execute, and write. Let's check it out. Awesome. We can see that the X has moved to the second set of RWX. Now let's set the skid bit with the command chmodg plus s* to include all the files. So we've set the skid bit on both files in our folder. They're now showing up with this yellow-orange background. You can see the letters S, and everything else is just like that. A lowercase s means there's an X underneath it, which means execute permission, whereas an uppercase S means there's no X, no execute permission. So, just like that, any user can execute the public executable file, but no one can execute the private executable file. To remove this skid bit, we type in the command chmod g-s**. Now, the skid bit is also used for folders when we want to enable group ownership permission inheritance. Let's look at some system files that have the swd bit set. For example, we've got the files path wd, ping, or su. These are tiny utilities that hang out in their respective folders, and they all have the swd bit set, as we can see. This is done so that everyone can run these files for their local tasks, but they actually run under the root user because the file owner is root. Now let's talk about the third special bit, which is the sticky bit. This one is applied to folders and is used to prevent file deletion in those folders. To set the sticky bit, we write chmod plus t and specify the path to the folder. For simplicity, we'll just use the dot to work with the current folder. Let's check result and look. The last letter in the first column shows us T letter, which means the sticky bit is set on this folder. Now that we've set the sticky bit, only the users who are specified as owners of the files can delete them from this folder. This is super useful for shared folders on servers, where anyone can drop their stuff without worrying that someone else will delete their files. To remove the sticky bit, we type chmod -t and the path to the folder. And there we see the T is gone. Now files can be deleted according to standard permissions. And by default, Linux has a standard shared folder with the sticky bit set. The folder is /tmp. You can spot the T here too. It's also present in nested folders. After talking about special bits and permissions in general, let's get into default permissions. You can check or set these default permissions with the command umask. Alright, let's remove all the files in our folder using the command rm. Now let's take a look at the current value of the mask. Let's type in umask, hit enter, and we see 0002. This is the current default mask. Now let's create a file using the touch command, and we'll notice it has some permissions. So the permissions that a new file gets are actually determined by that mask. In other words, with this current mask, we got those permissions for our file. Now let's change the mask. We'll enter umask, say 333, hit enter, and create another file. And now, check it out, its default permissions are different. The mask has changed. If we change the mask again and create another file, this next file will have yet another set of permissions. Basically, the mask works like this. From the maximum permissions, we subtract the mask, and what's left is the permissions that apply to the new file. Also, keep in mind that if we close our session or close the terminal, or disconnect and then reconnect, the mask resets back to default. And here we see that the mask is 002 again. Let's create a file, and we can see it gets the default permissions applied. In this section, we talked about access rights, managing them, viewing information, using commands like change mode, change owner, change grp, and special bits like swd bit, sticky bit, skid bit, and the umask command. So, we've already touched on the conversation about inodes a little bit in this course when we talked about the df command. We ran it with the h option to make the output more readable and informative. Then we added /, which filtered the output so that we only looked at stuff concerning our main hard drive. After that, we checked out the I option, which is about inodes, showing us how much of our drive is being filled up in percentage terms based on used files and inodes. And we mentioned that it's also a parameter worth keeping an eye on. Now, there's a related topic to this, which is links. In Linux, you have different kinds of links. Soft links, hard links, and we're going to sort through them now. To create links, we use the ln command. So, executing ln will give us info that this command is used to create links between files. First, let's clean up our folder and create a few files. For example, we're going to use echo to send some text to a file and we'll call it main config file. Let's make sure that file is created. Now, we're going to create a link. In this case, a hard link to that file. We can do that with the command ln. Next, we type the name of the file we're linking to, a space, and the name of the link file. We'll call it hard link to configs. Then we'll check that our new file is created with the ll command. Now, let's create a soft link too. Again, we'll use ln, but this time with the S option. S stands for soft or symbolic link. So we type ln-s, the name of the main file, then a space and the name of the new link file. We'll call it soft link to configs. All files are created. Awesome. Sometimes people get a bit confused between links and a file copy. To clarify that, let's create a copy to our main config file, and we'll call it copy of configs. Alright, everything's set up. And now let's see how it all works. If we just output the contents of each of these files, it might seem like they all share the same text. But first, let's clarify that a copy is not a link. A copy is a completely standalone file. We'll prove that next. Let's add a new line to our main config file. We'll echo some text into that specific file. Checking it now, what do we see? In the fifth column of the ll output, the file size is noted. You can see that the size of the main config file increased. The hard link to config size also went up, but the size of the copy stayed the same, and so did the soft link's size. For now, we'll just observe that, and we can draw conclusions later. So we added another line to our initial main config file. Let's now output the contents of all these files. In the main file, the line showed up. In the hard link, that line is there too. In the soft link, the new text appeared as well. But in the copy, there's nothing new, and there can be, because the copy only holds the contents at the point it was made. Next, we manage the copy and the main file separately. Now, let's dive into the difference between links. Specifically, between hard links and soft links. If we rename the main file now, let's see what happens to the links. So we've got this command here, mv main config file space and a new name. Let's just call it configs. Now let's check the outcome. When we look, we see that the soft link is showing up in red font, which is kind of a hint. Let's output the contents of the main file configs, the content of the hard link. Now, let's try to display the contents of the soft link, and guess what? That file is broken. It's not working. Soft link stops functioning after we rename the main file. Renaming doesn't affect the hard link at all, because the soft link is searching for a file with the specified name. And if it can't find it, it just doesn't know what to display. But if we give our main file its old name back, the one the soft link is waiting for, the soft link will start working again. Check it out. mv configs space old name main config file. Enter. Let's check the result. The soft link is displaying correctly again. Let's pull up its contents. Everything's working. It's all good. Now here's a question for the experts. What do you think? Will any of the links survive if we delete the main file? Let's execute it and see. rm main config file. You can see the file is gone. It's just not there anymore. The soft link is showing up in red font again. Let's peek into the contents of these files. The hard link is still working just fine, but the soft link is broken again. Well, the copy is leading its own life, But you can work with the hard link just fine. We can edit the file, open it in Nano Editor, add a new line, save it and exit. There's the new line showing up in the file. Everything's alright. You can work fully with the hard link even after deleting the main file. To wrap things up, here's what we're going to do. We will delete our files and recreate them. We'll check the command history for the numbers of the commands we used to create these files, and repeat our commands with numbers 624, 626, 28, 30, and 36. To repeat a command by its number, we just type an exclamation mark and the command number. An exclamation mark followed by 624 will repeat the echo command. An exclamation mark followed by 626 will repeat the command for creating the hard link. 28 is the command for creating the soft link ln with the S flag. 630 is the command to create a copy, and 636 is the command for adding a new line. Awesome! There, all our files are back in place. And now in the ll command we'll add the I flag to show those inodes. Inodes are the file numbers. Now we can see another column at the beginning filled with numbers. Those are the file numbers. Let's note that the number for main config file matches the number for the hard link. The number for the soft link is different. And of course the copy has a different number too. The access rights also match for the main file and the hard link file. The soft link formally shows maximum permissions, but actually when accessing the soft link, the permissions of the main file will be checked. We can visualize working with links like this. For example, let's say we have our disk, some Linux file system, and we create our main config file inside it. We add some content there, and now main config file looks at that spot. Later we created a hard link called hard link to configs. This new file points to the same spot on the disk that has a specific number assigned to it. Then we made a soft link. The file soft link to configs is looking at the name main config file. Now when we later made a copy, here's what happened. We took the contents of our file and duplicated it into a new file with the same content. So copy of configs is its own separate file, pointing to a different location on the disk, which we'll say has its own number n2. Now, if we somehow change the content of our main file, it won't touch the copies, but it will affect all the links and obviously the main file itself. Later on we went ahead and deleted main config file, and this didn't impact the hard link, but the file soft link to config stopped working. That's because the link point to the file name became broken, which is why the soft link got messed up after we deleted the main file, while the hard link kept working just fine. However, if we make any changes to the copy, that also won't affect the main file or its links. This is how you can visualize it schematically. In this section, we discussed the following topics. These include inodes, the file numbering system in Linux, hard links, and soft links. The next important tool in the Linux terminal is input-output streams. Let's clean out our folder from files and remember that the echo command lets us display some text on the screen. So, why does this text show up in our terminal? Well, that's because the terminal is the default output device. But actually, we can change this output device. That means if we use the echo command to write some text and then point it to a file with a right arrow before hitting enter, nothing will show up on the screen, and instead, a file with the name we designated gets created. And now that text is in our file. Let's do the same thing and create a couple more files with some random text, like report 2021 and report 2022. And just like that, you can see that all three files are there. You can check out the contents of these files using commands like more followed by file names. Speaking of input-output pipelines, let's also touch on the utility called cat, like a kitty, but not really. Cat is short for concatenate, which means to join strings together. In simplest terms, the cat command lets us display the contents of files like cat report 2020, but there's so much more cat can do. Specifically, when we use the cat utility, we can give it a bunch of file names separated by spaces. Then we'll get the combined content of those files right on our screen. Cat, being like concatenate, joins up all the content from those files we listed. You could even write cat asterisk and get all the combined contents of every file in our folder. Or cat r asterisk to get all files starting with the letter R. In our case, it's the same thing. We can also redirect streams here, like sending the output from the cat command not to the terminal but into a file. So, for one of the previous commands, we just add a right arrow, the name of the file, and hit enter. And now we don't see anything on the screen because the result of the cat command has gone into that file we specified. Here's that file, United Report. Let's pull it up. You can display it with the cat command or any other way that's convenient. Also, the cat command allows you to enter text into a file right from the console. Here's how that works. You just type cat, then a right arrow, and only after that, the name of the file. Hit enter and then it waits for you to type something in. You type in text line by line. Every time you hit enter, that new line gets sent to your file. This goes on until you press Ctrl D. You can also end the command with Ctrl C, but Ctrl D is the more proper way to do it. Okay, let's have a look. We see that we now have a file called consoleinput.txt. Let's print this file to the screen and yes, that text we typed in is now in this file. What do you think will happen if we run the same command again, cat? Right arrow, the same file name, and keep typing. So here's the deal. This new text, where is it gonna go? At the end of the file? Or maybe at the beginning? Or are we just replacing what was already there? Let's think it over and check it out together. So what we see is that our text has overwritten the previous content of the file, because the single right arrow first clears the file, if it exists, and then starts writing to it from a clean slate. But, of course, we can also append text to the end of the file. To do this, we type cat followed by the double right arrow, then the file name, press enter. We type some text. We'll wrap it up by hitting Ctrl D. Now let's see what's in the file. And now we've confirmed that the text has been added to the end of the file. So the double arrow pointing right adds to the end of the file, while the single arrow pointing right empties the file and starts writing into it. Also, let's remember the find command from past lessons. It helps us find files we're looking for. In the simplest form, you just use find followed by a pattern, like the file name pattern. Let's say it's something like asterisk.txt. And boom, it shows us all the text files with that extension in our folder. Or maybe we'll try find report asterisk. That means all the files that start with the word report. We can check our folder to see these files are really there. Of course, we can also search outside of our current folder. In that case, we'd say find followed by the path to the folder we want to search in, like /, which means we're searching from the root of the file system, wanting to dig everywhere. But in this case, we need to specify the name pattern with the -name key. Let's say we want all files with the sh extension, which are bash scripts. Using the key -type, we can specify the type of object we're looking for. The value D stands for directory and F for file. We hit enter and it throws a bunch of lines on the screen. But hey, we already know we can redirect that output into a file. Let's do just that. So, for the last command, we'll add an arrow to the right and the name of a file. Let's call it bashfiles.txt. Hit enter and it keeps throwing things onto the screen. But when the command finishes, we'll find that file bashfiles.txt, and inside it we'll see the results of the command. But what was it showing us on the screen? If we take a closer look at that output, it's all error messages. We can see that bashfiles.txt holds the results, while all the errors got dumped into our terminal. But guess what? We can also redirect the error stream. We can do that using this syntax. If we specify a 1 after the command, then the arrow to the right with the file name, and then a 2 and another arrow pointing to the right followed by the name of the new file. In this case, the command's output goes into bashfiles.txt, while any errors that pop up during execution go into error.txt. Hit enter and look, nothing shows up on the screen this time. Instead, we end up with 2 files from the commands run. We can peek inside these files to see that bashfiles.txt only lists files, while error.txt contains just the error messages. We can also glue these 2 strings together, the first and the second. To do that, we write the command like this. After the command, you put a 1, then an arrow to the right, followed by the file name, then a 2, another arrow to the right, and then that little ampersand one. So 2 arrows to the right and an ampersand one means we're sending the second stream to the same place as the first one. Just hit enter. Let's check the result. We see that we've got a brand new file. If we peek inside, we can see that it has both the result of the command and all the error messages all mixed together. The 2 streams have been glued together and sent to this file. It's probably more convenient to take a look using the head command with the file name just to pull up the first 10 lines. Among those lines, you will find both error messages and the results from the command. Everything is pretty clear here. Let's draw a little bit to visualize what just happened. When we kick off a process, it gets its own number and other attributes, or you can call it whatever you want, it doesn't really matter for now. We can pass in some parameters, keys, options, and so on when we start this process. And we can also send a data stream as input to our process. That's called the 0 stream. Next, while the process is running, it also generates some data. That's basically the whole reason why we started the process in the first place. This data goes into stream number 1. The first stream is the result of our command. If any errors pop up while the process is running, they go into stream number 2. By default, the first and second streams just get dumped right into the terminal. But we can control these streams, which is exactly what we've been doing with the last commands. We send the first stream to one file and the second stream to another file. That's what managing input-output streams is all about. To discuss the command processing pipeline, we need to bring back our text of the poem Romeo and Juliet. Since we deleted it, we'll download it again. This time we're going to use a package called pandoc. But first we need to install it. You can easily do this with the command sudo apt install pandoc. Pandoc is a utility that converts files between different formats. After installing it, we'll download our Romeo and Juliet poem from the web page using the pandoc command with the T option. We'll need the plain text option for our purpose. We'll specify the path to the HTML page. And we'll say that the result should be saved in a file called romeopoem.txt. Just hit enter. Great, the file is there now. Along the way, let's also get familiar with another utility called wc. That's short for word count. It counts the number of words. You can pull up the help for this command. In general terms, it allows you to check the file size in various units of measurement. You can see the size in lines, words, bytes, characters, and so on. We're going to need this utility. To see how it works, we'll run it with different options. In its simplest form, word count followed by the file name will give us various numbers that show the file size. Next, we'll run word count with the options L, W, and C. L stands for lines, so it will count the number of lines. And we see that our file has just over 6,000 lines. W stands for words, and C means bytes. we can say that our file is approximately 146 kilobytes in size. Now let's get back to our Romeo and Juliet poem. We can display the content of the file on the screen using the cat command followed by the file name. But right now, we want to explore the command processing pipeline, so we'll count the number of lines in this file like this. We'll use cat followed by the file name, but instead of displaying it on the screen, we'll pipe it using the vertical slash symbol. We'll pass the results of this command into the next command, word count with the L option. And there we see that our file has about 6,000 lines. We got the same result when we ran word count with the L option and immediately provided the file name. But in this example, we did it using a pipeline, which is represented by the vertical slash. You can also use the pipeline to facilitate viewing of file content that is split into pages. It would look like this: cat followed by the file name, then the vertical slash as the pipe symbol. And finally, we'll pass the output of the command into the command more. Hit enter. Now you can scroll through the pages using the spacebar. Press Q to exit back to the terminal. Another scenario for using the pipeline. We know there's a simple command ls that lists the contents of our folder. However, if we pipe the results of the ls command to the word count utility with the option W, we get a number 9. What does that number 9 mean? It indicates the total count of files in our folder. Why does this happen? The result of the ls command is like a string of file names. And these file names are separated by spaces, just like words in a sentence are separated by spaces. The word count in our case takes this string and counts the number of words in it because we ran it with the -W key. So the number of files in our folder is the same as the number of words in this hypothetical string. Let's consider another example. Suppose we need to recall a specific option in the history command. How do we clear the command history? Well, let's just say we've forgotten how to do that. We could spend a long time scanning through the full documentation looking for the right option, but that's not really convenient. This is where our trusty pipeline can come to the rescue again. If we type the command like this, history -- help for help, we won't actually run the command. Instead, we'll pass it through the pipeline, using a vertical slash to the grep command, which can search through lines, and specify that we're looking for the line containing the word clear. Press enter. Now we've received just the line we need, which indicates the option -C. Previously, we also talked about the find command. It allows us to find files by their names. For example, let's display all files with the txt extension in the home directory. Let's have some fun with the pipeline here as well. We'll pass the results from the find command through the pipeline to the head command to keep just the first 10 lines from all the search results. Then, let's say we want to sort our results. We can pass them further down the pipeline to the sort command. After that, we might want to keep only unique lines. Then we can pass those to the unique command, and when we want to count the number of lines remaining. Finally, we pass the results into the word count command with the key -L, which stands for lines. So the number of lines is 10. Then we might decide to save the results to a file. In that case, we'll use the right arrow, specify the file name, and hit enter. Now we have a file named linescount.txt. We can display its contents on the screen. It will show 10. In these examples, we've repeatedly passed the results of one command into the next command. You can build such a pipeline quite long. Perhaps we want to sort the search results and send them to a file. We can do that with this approach. Find the required options vertical slash the sort command, right arrow, and the file name. We can see that a file with that name has appeared. Let's dive a bit deeper into the grep utility. Grep is actually short for a global regular expression print. This command allows searching through lines, including the contents of files, using regular expressions. Let's keep practicing with the pipeline. Let's say we need to find out how many times the surname Montague appears in our file Romeo and Juliet. So we build the following structure. We get the contents of the file, for example, using the cat command, and pass it the file name. Next, we pass it down the pipeline to the grep utility to look for the word we need. Then we take that result and pass it through the pipeline to the wc utility with the key -l, and we see the number 28. Let's similarly count how many times the surname Capulet appears in this file. We'll write the same structure, just replacing the surname. It's really important not to misspell the surname. In this chain of commands, we've seen the result from the first command cat and the final result. Now let's take a look at the intermediate result that we get after the grep command. We'll execute it just like this, and we can see that it only returns those lines that mention the surname we're interested in. This text is what we fed into the word count command with the L option. In the grep utility, there's also the O option, which means it will show us only the matching string and nothing else. Here's how that will look. Using a command pipeline is also convenient for analyzing logs. In Linux, our logs live in a file located at /var/log/syslog. You can open that up to see it's filled with a lot of letters. Let's count how many lines are in this file. You can try to build the necessary command in the pipeline on your own, and we'll do it together as well. We'll pass the content of the file into word count with the L option, and we see that there are just over 3,000 lines in our log file right now. When we talk about log analysis, we often look for mentions of a specific service, word marker, and so on. For example, let's search for mentions of the SSH service in the logs. We'll do it like this. We pass the log file's content into grep through the pipeline and look for the SSH line. Here are the results. Or maybe we want to look at the logs for the cron service. Then we pass the file content through the pipeline into grep and search for the word cron. Or we could look for the system process, and so on. I think you got the idea. Also, nothing stops us from passing the filtered results from the grep command further down the pipeline to filter them again. For instance, we might want to keep only those results that mention the user root. In that case, we'll send it to another grep with the string root. Now we have a few less results. In our case, there are 199 lines. If we want to send the output of a command at some stage to a file, we can use the right arrow followed by the file name, then hit enter. And the file is created with the corresponding results inside. To summarize our talk about pipelines, let's recall the picture we drew discussing input-output streams. We talked about how a process takes in stream number 0, generates stream number 1 during its work, which is the output, and stream number 2 for errors. In a command processing pipeline, we manage streams 0 and 1. Thus, after a certain command, we send the first stream to the next command's input, making it the 0 stream there. For the next command, its first stream, the result of its work is also routed to the next command, where this data becomes the 0 stream again. So, we keep passing things along the conveyor until we hit enter to get the final result. That's what's called a command processing pipeline. Now, let's talk about another topic. This one's about the conditional command chains. Here's how it works. When we use the echo command to display some text on the screen, we only get that text. But what if we add a double ampersand and then we add echo by? What do you think this whole command will output in the end? In this case, it will output the word I and also by. However, if we replace the double ampersand with double vertical bars, then it will only show the word hi. Let's break down how this works. The double ampersand acts like a logical AND. Here's how it functions. The first command runs, and if it executes without any errors, then the second command runs too. So basically it's about executing the first command and then executing the second command. Now, the double vertical bars represent a logical OR. Here is how that operates. The first command runs. If it doesn't produce any errors, nothing else happens. Only if there are errors during the execution of the first command does the second command execute. Let's consider more practical examples rather than just displaying some abstract words. If we want to show the contents of our file or indicate that an error has occurred, we would write a command like this. For simplicity, we could use head, followed by the file name, double vertical bars, the logical OR, and then we write an error message. Now, let's execute that. Everything looks good. What do we see? We can see that the head command executed and displayed the first 10 lines of the file, and the echo command, the error message, didn't run because the first command was successful. Now, let's introduce an error in this command. Imagine we misspelled the file name. Let's start it with a capital R. We know we don't have such a file since Linux is case sensitive. So, in this format, where the file name begins with a capital letter, all of this command chain will behave differently. Hit enter. Look, we didn't get the content of the file because the head command threw an error. Therefore, the second command echo ran, which gave us the error message, error reading file. So, if there is an error in the first command, the second command will run. Let's apply similar logic using the double ampersand. We'll display the first 10 lines of the file's content, and if everything goes well, we'll output the word done. Everything worked perfectly, and it displayed done, which means everything is ready and done. Now, let's introduce an error in the file name, change one letter, and run the command. What do we see? We see that an error message is displayed, the contents of the file were not shown, and we also didn't see the word done, because the second command, echo, didn't execute. That's because the first command failed. Here's another practical example using conditional command chains. We have the command sudo apt upgrade. This command performs updates. In one of the future topics, we'll dive deeper into the apt utility and its commands. For now, let's just look at one example. So, before running the upgrade command, we need to execute the update command. That means we should first run sudo apt update, and only if that command succeeds. Then we should run the command sudo apt upgrade. This gives us the structure of sudo apt update and sudo apt upgrade. Enter. We're prompted to enter a password to run the first update command. There it goes. Next, it starts executing the upgrade command. Ultimately, it will ask us for confirmation with yes or no. I'll go ahead and say no because we're not too interested in the actual update process right now. We just needed to look at the example of the command with double ampersands. Let's leave that command on the screen as a commented example. In general, we can also construct longer chains like this, so we don't have to limit ourselves to just 2 commands. We can write multiple commands following the same pattern. One command double ampersand, second command double ampersand, third command, and so on. In this section, we discussed important tools such as links, inodes, standard input-output streams, and command processing pipeline. On every server, one of the key tasks is to keep an eye on its condition. This helps us check whether we're running low on RAM, whether disk space has run out, and which processes are hogging all the CPU time. Every operating system has the right tools to handle these tasks. Right now, let's talk about those tools in a Linux terminal. We'll kick things off with the top utility. This is essentially a terminal task manager. First, we'll launch the utility, get familiar with the main elements of the interface, and then discuss its capabilities. In the terminal, we type top, hit enter, and we see a table displaying the running tasks. At the top, there's a header that gives us a summary of the server's status. The main part of the screen shows the currently running tasks. Let's break down what we see here. In the first line of the header, we have the utility's name, the system time, the uptime of the server, the number of logged in users, and an interesting line that says load average. After the phrase load average, we see 3 numbers. These represent the average load on the server over the last minute, the last 5 minutes, and the last 15 minutes. We can compare these numbers to understand how the server's load has changed over time. This method is very resource efficient because calculating 3 numbers takes considerably less time than creating graphs. So, We can use these three numbers to gauge how the CPU load has varied over the last minute, 5 minutes, and 15 minutes. In the second line of the header, we have information about the number of running tasks. It tells us how many there are in total and how many are in different statuses. It's also helpful to explain what these process statuses mean. As we know, when a process starts, it gets assigned a number. This number is stored in the PID attribute, which stands for process identifier. It's a unique positive integer assigned to each process. When a process starts, it immediately goes into a sleeping state. S means sleeping. In this state, it's waiting for us to give it a command. At some point, we might ask it to copy a file, compile some code, or encode a video, and that's when it switches to a running state. This is when it's actively performing our command, spinning away. Once it finishes our command, it goes back to the sleeping state. Between these two states, it keeps cycling through until we decide to terminate the process. For example, when we click the close button in a window. So, what happens next? First, the process will be unloaded from the RAM, and then it will be removed from this list of running processes. Now, there's a temporary state called zombie. If a process is in the zombie state, it means that it has already been removed from memory, but it hasn't yet been cleared from this task list. Eventually, it gets removed from here as well, and then we just have a record of it left, in a sense. These are the main states our processes can be in. The third line contains various magical indicators that, if you know them, can help you understand how much CPU time is being consumed overall, by user tasks or system tasks, how much time a process is waiting to write to disk, and similar details. The last two lines are about RAM, specifically about RAM and the swap file. I think it makes sense to explain a bit how RAM works in conjunction with the swap file. We know that modern operating systems are all multitasking. This means that we can load one process, another process, a third process into RAM as long as we have enough memory available. At some point, we might want to start a new process that won't fit in RAM anymore. That's where the swap file comes into play. You can think of it as a sort of virtual extension of RAM. But in reality, it's just a file on the disk. Typically, the size of the swap file is set to double the size of the RAM, but you can adjust this in the operating system settings. So when the operating system runs low on RAM, it starts offloading some data to the swap file to free up RAM for a more important process. And that's how it works. Here's a key takeaway. A swap file is a file on the disk, as we mentioned. And no matter how fast the disk is, it will always perform slower than RAM. Thus, if data processing is happening through the disk instead of RAM, it can lead to significant slowdowns in server performance. We can extract this information here. We can see the total amount of RAM, how much is used, and how much is free. The same goes for the swap file. We can check its total size, free space, and used space. Now, let's discuss the main columns in our top utility table. The first column is PID, which stands for process identifier. The second column is user, the name of the user who started the process, because each process is always tied to some user account upon launch. Next is the PR column, which indicates priority, or the process's priority level. The higher the number, the higher the priority. And RT in this column means real time, which indicates the highest possible priority. Next, it's worth noting the VIRT column representing virtual memory or the total memory allocated to a process. The RES column is for resident memory, which is the portion of RAM allocated to a process that will never be swapped out to the swap file under any circumstances. SHR stands for shared memory, which is the memory shared between processes. The S column indicates the state or status of our process. What is it doing? Is it stopped sleeping, working, or in a zombie state? %CPU shows the CPU load, while %mem shows the memory usage. Time indicates how long the process has been running. Finally, the command column represents the command that initiated the process, either in a concise or detailed manner. To exit the top utility, we simply press the Q key. Q stands for quit, just like in other programs. You can also run the top utility with certain options to automatically sort the output right away. For example, using top-O followed by the column name PID will sort all processes by the PID field immediately. Let's check that out. Now we can see that all processes are sorted, in this case in descending order, since we're typically more interested in the most recently started process. And interestingly, that process is actually the top process itself. Or let's run top with the default sort by the user field. That would be top-O user. You can observe the result. If we want to run the utility with sorting in reverse order, we would type top-O column name. Just like that. Now, all our processes are sorted in ascending order. Let's press the Q key to exit. We can also try launching the top utility with sorting by the command field, for example. A key point is that we write the field name in uppercase here. Now we can see that the entire table is sorted by the command field. Let's exit the top utility and run it in the simplest way, without any sorting. Now, let's discuss some of the features of a top utility regarding how the displayed information can be formatted. For instance, if we press the C key, the display of the command column switches from a compact view to a detailed view. Pressing C again toggles back to the compact view, and pressing C once more brings back the detailed view. The detailed view gives us the full path to the process we launched, along with any options we used, as long as that information fits on the screen. There's also a hotkey capital V or Shift V or Caps Lock V, which needs to be pressed. In this case, the command column is displayed in a tree format. So this gives us the option to switch from a tabular display to a tree view and back. Here we see the command column displayed as a tree. You'll notice that the systemd process is process number 1. It serves as the root of this tree. In fact, in Linux, the systemd process is the very first process that starts when the operating system boots up. We can see that happening right here. The Z key lets us toggle the information display from monochrome to colored, which might be easier to read. Pressing the M key switches the memory information display from text to graphical format, and vice versa. You can also sort processes by their columns even while the top utility is running. For example, pressing the uppercase letter M sorts by the memory field in descending order. The capital P sorts by CPU usage. The uppercase letter N sorts by the PID field. And the capital T sorts by the time field, which displays the running time of the process. You can even start the top utility directly with process filtering, for example, by user. So basically, if we add -u and the username, let's say it's sales guy, it'll show us only the processes from that user. Right now we don't have any processes running under that user. So we'll open up another terminal window, log in as sales guy, open something like the Vim editor, and then start working. Now we can see in the main terminal window that there are processes running under sales guy. It's just the beige terminal and the Vim editor. Let's exit the top utility and relaunch it without any extra filtering options, just to show that you can filter even while top is running. To do that, we'll hit the O key and type in our filter. For example, user equals sales guy. It's important that the column name is in uppercase and the value is in lowercase. Like this. We hit enter and now it shows us only the processes from that user. Pressing equals will reset the filter. Or we could add another filter. We hit O to start filtering. Let's say we type command equals Vim. Hit enter. And now we only see one line with the Vim process running under sales guy. Press equals again to reset the filter. Also, the top utility can kill a process. Let's run the Firefox browser in the user interface, for example. Here's the window that popped up. Now, we'll find the Firefox process in top. Sure, you can scroll with page up and page down to find the process, but it's easier to filter. Hit O, type in the filter, command equals Firefox. Hit enter, awesome. To kill the process, we press the K key, which is short for kill. Next, we need to enter the PID of that process. For Firefox, in our case, that'll be 3557. hit enter. Then it asks for a signal. We'll type in number 15, and later I'll explain what signals are for processes. Hit enter and we see that the Firefox window disappears. But there's a short period where the process still shows up in the list of running processes, even though it's not in memory anymore. At this point, it's a zombie and will disappear from the list shortly. In a couple of seconds, Firefox is gone and it's not showing here anymore. You can press equals to reset the filter. Let's try to kill the Vim process that's open in the middle window in a similar way. We hit O, type command equals Vim, hit enter. Now we see the PID, which is the number of the process we want. To kill it, we hit K, which means kill, enter the process number 3554, hit enter. 15 is our signal, hit enter, and then we get told, operation not permitted. So why couldn't we kill the Vim editor? It's simple. This process is running under a different user. The top utility is being run by IT guy, while Vim is running under sales guy. So, a user can only kill their own processes. You can't touch someone else's stuff. But of course, this restriction doesn't apply to the root user. So, if we run the top utility as root using this sudo prefix right now, we'll have full access to everything. Let's see for ourselves. We'll exit top and then enter it again using sudo top. If we're prompted for a password, we enter it, hit enter and follow the same steps again. To kill a process running in the Vim editor, we'll first need to filter it. Press O, input, command equals Vim, enter. Now we see the process number. Next, we hit the K key. We enter the process number. We'll use signal 15. Hit enter. And this time we successfully terminated someone else's process because we were doing it as root. We can switch to a second terminal window to confirm that the Vim editor is no longer running there. Of course, we can start it again and there it is showing up. And this new process will even appear in our list of running processes, but it will be a completely different process. In other words, this new process has a different number and all its other attributes. Let's close the second terminal window and take a moment to explain a bit about process signals. We'll exit top and type kill with the L option in the terminal. We have the kill utility, which we'll come back to a bit later. The L option allows us to list the signals, meaning a signal to a process is just a specific number. This number ranges from 1 to 64 in our case. A signal to a process is essentially an option we use to terminate that process. Let's discuss the popular ones. For example, there's signal 15, which we just used. Signal 15 can be compared to what a user does when they click the X button on a process window. What does that mean? It's a polite, civilized way to end a process. We're essentially telling the process, please terminate, unload from memory once you've finished your current operations and saved any necessary data. That's the equivalent of signal 15. There is another option for a more forceful termination of a process. If, for instance, we find a process in the tree of running processes and choose to kill it instantly, meaning as fast as possible without saving data, without allowing it to finish current operations, and so on. That's akin to signal 9. These are the two most popular signals. There are also signals for pausing and resuming processes, among others. Let's talk about another task manager in the Linux terminal called htop. If we type htop, we'll probably find out that this utility isn't installed. But don't worry, it will suggest a command for us to install it. For instance, you might see something like sudo apt install htop. So you just copy that command, hit enter, and in a few seconds, htop will be installed. Once we get the command prompt back, we type htop again and hit enter. Now we get to see a more visually appealing and user-friendly version of the top utility. This is htop. Here, we have a header with summary information and a table showing the running processes. Everything is displayed a bit differently. For example, at the top in a graphical format, we can see a list of CPU cores. In this machine, I've allocated 3 cores. Looking at them, we can see they aren't very busy at all, let's say. From analyzing this information, we can conclude that for this particular server, we could actually reduce the number of cores given the current load. A bit lower, there's information about RAM and the swap file. This is shown right away in a graphic format, which is a bit clearer than what you see in the top utility. On the right, we have a list of tasks showing how many there are in total and how many are actively running. Load average, that's the average load, which we already know. Uptime, this shows how long the server has been running. In the main table, we can also use the mouse to highlight the desired process or column to sort based on that column. At the very bottom, there are hints for hotkeys. F1 is for help. F2 is for settings. F3 is for searching. F5 lets you switch the view to either a tree or a list. One crucial difference is that the exit from the htop utility is done with the F10 key. In htop, you can also terminate processes. Let's launch our beloved Firefox. We can find it within the list of running tasks. For example, we can press F3 for search, type Firefox and hit enter. And just like that, the cursor moves to the line with Firefox. We can scroll it up if we want. If we click on it with the mouse, all of its child processes or threads can be expanded or collapsed. After that, we also press the K key to terminate the process. In this case, an additional column appears on the left, from which we can select a signal with the mouse. You can choose signals like 9 or 15, depending on what we need. Select it and hit enter, and voila! The Firefox process is terminated. It is no longer in our table. The window has disappeared as well. If we compare top and htop, overall, they offer roughly the same capabilities, but htop is just cooler, trendier, and more youthful. Htop supports both vertical and horizontal scrolling, meaning you can navigate with keys. It also works with the mouse. To kill a process in htop, you just highlight it with the mouse and then press K. These utilities have different hotkeys, and likely, htop will need to be installed separately, while the main top utility comes pre-installed with most distributions out of the box. The exit from the htop utility is done with the F10 key. To get information about the process, a list of running processes, or even to end a process, we don't always have to rely on the top task manager. There are simpler commands for that. Let's talk about them now. For instance, there's a utility called ps. This command, in its simplest form when typed without any extra parameters, will show us information about the current process. For example, right now, we have the bash terminal running. You can also pass the PID of a process, which is basically the process number, as a parameter to the ps utility. Typing ps1 will give us information about the process with number 1. Using ps with a different number will show us info about that specific process. The ps command also has some keys, specifically aux the 3 letters A, U, and X. When you use it this way, it will list all the running processes in a table format. It looks quite similar to what we see in top, but in top, the information gets updated periodically. Recalculations take place. Here, however, we get a snapshot, static information that won't refresh. But you can still see process numbers, statuses, who started them, and more. Let's launch the Firefox browser again and use the ps utility with the AUX keys to find the line for the Firefox process. We can use a pipeline for this, so if we type psaux followed by a vertical slash, and then use the grep utility to filter out just the lines mentioning Firefox. Press enter. We see a lot of information because, in reality, the browser starts with several child processes and threads. The very first line in our case, its second column, contains the number PID of the main Firefox process. That's 5130 for us. Let's remember that, and now we'll end it. Once we have the number of the process we want to terminate, we can use the kill command. So it's kill, followed by the process number, then hit enter. That's it. It's gone now. If we try to find the Firefox process again, we won't get any results. The kill command can also accept a signal number as an option. With the S key, we can write the signal. It could be 9, 15, or some other signal. In our case, the process with number 5130 is already ended, so the command won't execute. But if a process with that number were running, we could end it by specifying an additional signal. But what should we do if we want to terminate a process, knowing its name, but not its PID or number? Here, the PID of utility can help us. A brief one-liner about this command tells us it's used to find a process number by its name or part of its name. Let's launch Firefox again and type PID of Firefox in the terminal. It will return several processes because the browser usually runs with a set of many processes, child processes, threads, and so on. Among the listed processes, we look for the one with the smallest number. That's 5818 for us. Now we can end it again. We'll type kill, let's say with S9 passing in signal 9 and the process number 5818. Press enter and that process is gone. If you want, you can minimize the terminal window to see that the browser window has also disappeared. Right now, if you type beta Firefox again, you won't get any results because we no longer have any running processes named Firefox. Let's discuss another important tool in the Linux terminal for monitoring our processes and services. This tool is called systemctl. Systemctl is a utility that allows you to manage services in Linux. In its simplest form, if you type systemctl and hit enter, it will display a complete list of services available on your machine. You can scroll through this with spaces until you reach the end. If you type systemctl status, you'll get a tree-like list of all services with a header at the top that provides some summary information. In this view, you will only see the services that are currently running. Let's count how many services we actually have on our machine. You would type systemctl, a vertical slash, wcl using a pipe, and there you have it. We see that we have 232 services on our machine, but most often we use systemctl to manage specific services. For example, there's the status command. So if we type systemctl status followed by the service name, let's say SSH, it will give us information about the service's state. Here we see that it's active, running, and all looks good. It shows the process number and other information too. We can also stop our service if we type sudo systemctl stop SSH. An important note here, if we are just displaying information about the system state or about a certain service, we don't need root privileges. However, if we want to manage it, meaning we wish to change its state, we run the systemctl utility as root. In this case, to stop the SSH service, we use the sudo prefix. After this, we will check the status again. Systemctl status SSH. And we can see that the service is not running. It's inactive. There's a small command also called isActive. Systemctl isActive followed by the service name will output one line indicating whether this service is active or inactive. In this case, our service is stopped, not active. Let's restart the SSH service using the command sudo systemctl start SSH. Now, let's check if it's active with a isActive command. Now the response says active. We can also check the status with systemctl status SSH. And again, it shows that the service is active, running, it's working, it has a number, and that it's listening on port 22. Now let's look at other systemctl service commands. First, we'll check the status of the cron service. There is a service called cron, which allows you to schedule tasks to run at designated times. We will discuss it further in upcoming sections of this course, and here we confirm that the cron service is running. Everything is good with it. Using the systemctl utility, we can also restart the cron service. This can be done with the command sudo systemctl restart cron. What does the restart command do? It stops the service, then starts it again, refreshing it with updated configurations. All the new configurations will be applied to the restarted service. An important detail to note is that when you use the restart command, the process ID, or PID, will change because the service is completely killed and stopped before starting it up again. However, if we want to reload the settings and apply them to the current process without restarting it, we have the reload command available. For example, if we enter sudo systemctl reload for the SSH service, we can apply all the updated settings for the SSH service without stopping or restarting it. If you look up systemctl status SSH, you'll see that the process number hasn't changed. You can observe this here. There are also enable and disable commands for the systemctl service. Using systemctl enable adds a service to the startup list. The disable command removes services from the startup list. Let's go through a few examples. For instance, if we enter sudo systemctl enable ssh, that command will set the SSH service to start automatically on boot. You can check this by typing systemctl is enabled SSH. This enabled command checks whether the service has been added to the startup, and we get a response, enabled, so the service is indeed active. The disable command removes the service from the startup. The command would look like this: sudo systemctl disable SSH, for example. Let's verify. By running systemctl is enabled SSH, we now see the message disabled, meaning that the service is off. This means it won't start automatically the next time our machine boots up. Let's add it back to the startup with the enable command and check again. Great! The systemctl utility also has a handy list units command. It allows you to display all the services regardless of their current state. You can also add the option -- type equals service and hit enter. Now you can see all the services available on your machine in a more user-friendly format. You can scroll through this list using the spacebar. If you want information on a specific service, you can add a filter. Just type the name of the service in quotation marks. For instance, SSH*, since we don't remember the exact service name. After hitting enter, you'll see information only about the SSH service. In this section, we discussed tools for monitoring server status in Linux. These include utilities like top or htop for task management, commands like ps, kill, pidoff, and the systemctl utility for managing services in Linux. Before we dive into discussing software management in Linux, let's take a moment to sketch out, basically, to visually represent what's happening in Linux regarding this topic. So, we have our fantastic Linux server, and it needs a way to get new packages installed, update itself, and so on. In Linux, software is referred to as packages, and these packages are stored in what we call repositories. Typically, these are remote cloud storage locations somewhere out there. Of course, you could set up your own local package storage, but most people prefer to use the standard cloud repositories because they cover most of our needs in this area. So we have a set number of repositories, and on our machine, we decide which repositories we will access, which ones we won't, where we'll get our software from, and which repositories we don't need. The utility that manages packages is called apt, at least in Debian-based distributions. This includes Ubuntu, Debian itself, Linux Mint, and so on. The purpose of these repositories is to unify software management, making it safer and ensuring timely updates for everyone. In other words, billions of Linux machines around the world go to these repositories for their packages, updates, and all that good stuff. This is super convenient and also helps save disk space across those billions of machines. Recently, in the world of Linux, a package system called Snap has also emerged. It allows for software management too, but it has its own entire infrastructure, its own repositories, its own package lists, and everything else. Snap cannot access apt repositories, and similarly, apt cannot pull packages from Snap's repository. They have different formats, everything is different. So, in a sense, it duplicates an existing infrastructure. But why do we need this? Well, the thing is, in the Linux world, there's what you might call a whole zoo of tools for managing software. A whole zoo of package managers exists. Each distribution has its own tools, which can be inconvenient for IT professionals, since they have to deal with different commands, slightly varying formats, and incompatibility issues. There's a growing idea floating around to bring all software management in the Linux world under one single interface, so that each distribution uses the same tool for this purpose. Snap is an attempt to realize this idea. At the moment of its implementation, it does create some additional inconvenience, essentially duplicating functionality. But if it all comes together in the end, everyone stands to gain. The current inconvenience is that, for example, if we want to check whether a specific package is installed, we have to look both in Snap and using apt. But overall, the trend is positive. On the bright side, Snap comes pre-installed in recent versions of Ubuntu. Alongside Snap, there's another project in development called Flatpak. He's implementing basically the same idea. We'll see how everything develops, but ideally, this should make life a bit easier for everyone. So, let's take a closer look at our apt utility. Let's call up its help guide. Here, we're shown the main commands for this utility. Now, it's a good time to mention its older sibling, apt-get. Originally, it was apt-get that was introduced for managing software here in our distribution, but over time, they reworked apt-get into the shorter named apt, which also has a bit more advanced functionality. Overall though, they're pretty much the same, apt and apt-get. Let's discuss the main commands of this utility. For instance, there's the update command. Since we're well versed in English, we know the word update. So, one might think that the update command performs the update, but actually it doesn't. The update command, which has a somewhat counterintuitive name, actually prepares for the update. Specifically, it reads the package lists from the repositories that our machine is using. The actual update is done by the upgrade command. This command downloads all the packages and installs them on our machine. It's not an instantaneous operation. It will take some time depending on the power of our machine, the speed of our internet, and so on. But the upgrade command is the one that will perform the update. Next, we have the install command, which installs a package by its name. You can use the reinstall command if you need to reinstall, say, if something went wrong with a package. Then there's the remove command, which removes a package. And purge is another command that also removes a package. But they do this in slightly different ways. We'll clarify the differences through practical examples in a few minutes. In short, the remove command leaves all settings intact when it removes a package. On the other hand, purge cleans up everything related to that package. It removes all its files, all settings, everything. Another interesting command to note is the source command. It allows you to download the source code of packages if you need to rebuild or recompile them, or just take a look inside, and so on. There's also the download command. This one lets you download a package as a deb file, so you can move that file to another machine or install it using another utility called dpkg. We're going to talk about that one too today. Also, the last line of help gives a line about some kind of cow superpower of the apt utility. We'll get into that as well. So, let's switch to practice. We'll type in the command apt update and get an error message. We don't have permission to execute the operation because it's an administrative command. To run it, we need to specify superuser privileges, so we have to use the sudo prefix. Let's repeat that command, writing sudo in front with a space. If prompted for a password, we'll enter it and hit enter. Now, the command runs successfully. That is, the apt utility is currently reading the repositories and updating the package lists. To find out which packages need updating, you can use the command apt-list --upgradable. We'll see a long list displayed. Let's see how many lines are in this list. If we add a vertical slash to the last command and pipe the result to the wc utility with the -l flag, we can find out how many lines were produced by the previous command. And here we see that 281 packages need to be updated on our machine. If we decide to perform the update, we run the command sudo apt upgrade, and the update process begins. Since we didn't use the -y option to indicate that we agree with all prompts during the installation, we will be asked if we're sure we want to proceed with the update. I'll go ahead and type in, which means no. So, we won't execute the update and we'll move on. In other words, To avoid being asked anything during the update, we could have included the -y option. We won't execute this command. We'll just leave it here commented out. Now let's move on to installing commands. In fact, we've already used this in our course before. Let's review it once more. Let's say we want to use the htop utility. We type its name and realize it's not installed. So we go ahead and install it using the command sudo apt install htop. And just like that, the htop utility is installed. We can either look up its help or launch it. To exit htop, you press the F10 key. We remember that. And in the same way, we install the packages we need. Whether it's the MC package, which stands for Midnight Commander, or the tree utility that we've also installed, or the zip package, which is an archiver, it doesn't matter. The install command installs a package by its name. If we feel that we no longer need a package, we can remove it using the remove command. Now, to mix things up a little, let's use the apt-get utility to show that apt and apt-get are pretty much the same thing. We'll type sudo apt-get remove htop to remove the htop package. Since we forgot to add the -y option when we entered the command, we'll be prompted to confirm during the execution. We press Y, and in a few seconds, htop is removed. To avoid being asked anything while deleting a package, we'll specify the Y option right away. Let's remove the next package, zip. We'll type remove zip-y. Now, let's talk about some nuances of package removal. For example, we have the MC package, Midnight Commander. We can launch it to make sure everything works fine. Now, we decide to remove it. First, let's check the folder /etc/MC to see that it holds important files for this utility, including some configurations and more. And now, we'll remove it. We run sudo apt remove MC. There, we've removed the package. Let's check the contents of that folder again and confirm that all the configuration files are still there. As we mentioned earlier, the remove command does not delete configuration files. However, if we decide to remove a package using the purge command, such as sudo apt purge MC, then after running this command, we won't have any configuration files left. So if we later decide to reinstall the package that we previously removed with purge, we'll have to set everything up from scratch again. What we're talking about here is that if we remove a package using the remove command and later decide to reinstall it, all the previous settings will still be there from the last time we used it. Let's take another look at the documentation for the apt utility and remember the cow superpower. What's this all about? When we type apt-mu in the terminal, we're treated to a delightful depiction of a little cow, done in a CI art. And that's what we mean by the cow superpower. Programmers really enjoy references, and, in fact, there's another package manager called aptitude. Let's check if it's installed on our machine. In this case, it's not. Let's quickly install it, using the command sudo apt install aptitude and then peek into the documentation for aptitude. Right there, we'll see a nod to the cow superpower. At the very end, it tells us that this utility has no cow superpower. So, if we type aptitude mu, nothing special will happen. It won't show us anything. But you know we're still going to run that command anyway. And it tells us that there are no Easter eggs here. Also, the documentation mentions the -v option. This option allows you to output some additional information. So let's use it. When we run aptitude mu-v, it gives us the same message, but in different wording. The documentation also notes that the -v option can be used multiple times. Of course, we're going to take advantage of that. Let's add another v, then one more, and yet another. And at some point, specifically, when we use 5 v letters, aptitude will yield and show us its Easter egg. For those who recognized it, it's an elephant inside a boa constrictor from The Little Prince, which is a reference back to the original apt-mu. This really shines a light on how programmers love to include references. And this idea has evolved into a fun little package called cowsay. Let's go ahead and install it. We'll type sudo apt install cowsay -y and hit enter. Now we can type "cause" followed by any phrase, like hello or ciao or whatever else comes to mind. That was a fun little diversion, but let's move on to the next package, which is called dpkg, another tool for managing software in Linux. We've already drawn up a diagram illustrating how the apt utility works with repositories. We understood that apt can manage local packages and can also search for and retrieve these packages from remote repositories. But there's another utility that works with part of this infrastructure. It's called dpkg, short for Debian packages, and it can manage local packages, but only those that are already on our machine. dpkg doesn't have the ability to access repositories, so it's sort of locked inside our machine. However, the dpkg utility can install packages. For this to happen, the package must first be downloaded as a file with a deb extension, and that file can be downloaded using the apt utility. So, if we download a file with apt, we can then install that package using dpkg. This is particularly useful in situations where we need to transfer a necessary package in a deb file to an isolated machine, like one that's not connected to the internet, using, say, a USB drive. Let's go through some scenarios for how to use the dpkg utility. First, let's call up its help. The main commands listed here also hint that this is a tool for working with software. The option -I or install to install a package, -R or remove to delete one, -P capitalized or purge, -L or list, and so on. But all this work is confined to our Linux machine. In its simplest form, we can type dpkg-l, which means list, to display a full list of all the packages installed on our machine. You can scroll through this list with the spacebar, but let's take a moment to check its size. By hitting the Q key, we can exit and then rerun the command dpkg-l and pipe the results to the word count utility to count the number of lines. We see that we have about 1500 packages installed on this Linux server. The apt utility also has a list command with the key installed, which will also show us that same list. We can compare the sizes of these two lists. Let's print the size of the dpkg list and the size of the apt list side by side, and we can see that in both cases we have roughly 1500 packages. The difference of 4 lines is just the headers in the dpkg output. The apt list command without parameters will give us a complete list of packages available to that utility. This will include all packages from all repositories accessible to apt. This list is quite lengthy. Let's check its size using the familiar method we already know. We see a number around 80,000 packages. That's what's available for apt. Meanwhile, for dpkg, there's only about 1500. I highlighted these two numbers, so we can evaluate the difference between the number of packages available for dpkg and the number available for apt. The fact that these numbers differ by an order of magnitude clearly shows that apt can manage not just local packages, but also those found in remote repositories. The dpkg utility can also provide information about a specific package. If we say dpkg-l followed by the package name, for example, tree, will receive information about that particular package. We're shown a heading and a table that has columns with information about the tree utility. For example, there's the command dpkg-lmc, which displays information about Midnight Commander. In this case, we see an empty table at the bottom. This means that MC isn't currently installed because we removed it earlier. To display information about a package, you can use the command apt show package name. For instance, apt show tree will give us the details about the tree package. In the documentation for the dpkg utility, we also saw the key -I, which stands for install. This key allows us to install a package. However, dpkg cannot access remote repositories. Let's go through a specific example step by step to see how this works. First, we'll navigate to our folder called Linux course. Let's take a look at the files we have there right now. Next, we're going to download a new package, let's say htop. The command for this is apt download htop. Once the download is complete, we'll check the contents of our folder again. Now we can see a shiny new red file. This is the deb package for the htop utility. Since we've downloaded it to our machine, we can install it using dpkg. The command looks like this: sudo dpkg-i file name. Just press enter. In a few seconds, the htop utility will be installed on our system. We can launch it to double check this, and we'll exit right away by hitting F10. These are typical scenarios for using the dpkg utility. Now, let's take a look at the snap utility. We'll pull up the documentation for snap, and we'll see that the main commands suggest it's a tool for managing software. Snap comes pre-installed in the latest versions of Linux Ubuntu. But if you can't find it on your machine, you can install it using apt with the command sudo apt install snap. After that, snap will definitely be on our machine. Now, let's consider a situation where apt won't help and we need to use snap. Let's say we want to install the Opera browser. We'll search for it by typing apt search opera. This is searching within the repositories. We get a lot of lines here, but none of them are for the Opera browser. So let's look in snap instead. We type snap find opera, and we get a much more compact list of packages available in the snap repository that include opera in their names. In this case, the top 3 entries, Opera, Opera Beta, and Opera Developer, are official versions of our browser, and we can trust them. Now we can use the command snap list to see the packages that are installed on our machine with snap. This list is much shorter than what we saw with dpkg. Alright, since we found Opera among the snap packages, we'll install it using snap. We type sudo snap install opera. Notice that any commands that modify software on our machine need to be run as root, which is why we use the sudo prefix. But if a command is just viewing or outputting some information, you don't need root permissions to execute it. Specifically, the install command requires the sudo prefix, while the find or list commands do not. So, after a bit of time, we ended up with the Opera browser installed. We can check out the updated list of software using the command snap list and notice that there's now an entry for Opera. Let's go ahead and launch it. We type in Opera and hit enter, and after a little while, we see some logs being printed right here in the terminal, and a window will pop up. However, the Opera browser itself isn't really what we're focusing on right now, so we'll just close it. We've just confirmed that it was successfully installed. Now, as we can see, Opera is listed among the snap packages. But if we try to search for Opera in the dpkg package list by using the command dpkg-l opera, we won't find anything. Also, the command apt show opera won't show us anything either, because, as we previously illustrated in the diagram, dpkg and apt-am don't have access to the snap infrastructure. The opposite is also true, meaning that snap can't utilize the apt infrastructure. To remove a package from snap, we type sudo snap remove, followed by the package name, which in this case is our Opera browser. And of course, after removal, Opera is no longer in the list of installed software from snap. In this module, we're going to learn how to work with package managers. These tools allow us to install, remove, and search for the packages we need. But what do we do if we find out that the package we need is not available in the repositories? In that case, we might take a page from Windows Book. That means we would find the official website of the product we need, locate the package there, download it, and then install it. Let's take a look at an example with VirtualBox. Suppose we need to install VirtualBox on our Linux machine. Great! We head over to the official VirtualBox site at virtualbox.org. Next, we click on the Download tab. Here, we see that the package is available for Linux distributions as well. We click on it. Now, we're offered various packages for different distributions. There are options for Red Hat, Ubuntu, and other Debian-based distributions. Notice that the files have different extensions depending on which distribution we choose. When you hover your mouse over them, down in the left corner, you can see which file you might download, and the extension at the end will indicate the type. This is because different distributions might use different package managers, so the file extension corresponds accordingly. Since we're working with Linux Ubuntu, we'll download a deb file for our operating system, a file with the deb extension. You can right-click and copy the path to this file. Now let's switch to the terminal and check what files and folders we have in our current location before we download. To download the file, we can use the wget utility, for example. We type the name, paste the path to the file we need, and hit enter. It will start downloading, and soon we will have a file with the deb extension, which is essentially the package. This package can be installed using the dpkg utility, just like we did in previous lessons. Looking over, we see that a little red file has appeared. Let's go ahead and install it now. We type dpkg-i followed by the file name. Hit enter. Of course, remember to use root permissions, the sudo prefix, because installing software is an administrative operation. Press enter. If it asks for a password, we enter it, and the installation begins. What we just did is a typical Windows scenario for installing software. However, this method does have its drawbacks. At the minimum, it creates hassle with updates. For example, how do we know when a new version is available? We'd have to check the website every time to see if there's an update. That can be quite inconvenient. Then, even if a newer version of the package we need does become available, we'd have to manually download and install it again. In Linux, these operations for managing software are actually centralized and pretty automated, you could say. Right now, I suggest we remove the VirtualBox package that we installed using the Windows method and reinstall it the way it's commonly done in the Linux world. The dpkg utility has the -r flag, which stands for remove. After this, we can specify our package. Enter. Awesome! VirtualBox has been removed from our machine. Before we dive into how to install it correctly, let's take a peek inside the etc directory at the root of the file system and check out its apt folder. Inside, we'll find the file called sources list. This is a simple text file, and we'll display it on the screen now, for instance, using the cat command. So what do we see here? We can definitely confirm that this is plain text. In our case, most of the lines begin with a hash symbol. As we know, a hash symbol indicates comments in many programming languages, including in files that serve as instructions in a Linux machine. This sources list file contains a list of repositories that our machine works with. Specifically, the lines that aren't commented out are the active repositories that our Linux server accesses when we run sudo apt update or upgrade, depending on what we need. The commented outlines correspond to disabled repositories. Now back to the VirtualBox installation issue. In fact, it's possible to add the official VirtualBox repository, which would align the installation and removal of this package with the standard practices we typically use with the apt utility in Debian-based distributions. You can find this information on the official VirtualBox website, right on the download page. If you scroll down a bit, you'll find instructions for adding the VirtualBox repository. Adding a new repository involves two steps. The first step is to specify the repository itself. The second step is to add the key. Adding the key is important for security. It ensures we're accessing the legitimate site. In the simplest terms, we can just take a line suggested on the official site as the path to the repository and paste it directly into the sources list file, perhaps at the very end. This is a valid approach, but there's a more secure and standardized way to do this. In particular, we have the sources list D directory. Let's take a look inside that folder. Right now, it's empty. We can use the tree utility to display the contents of our directory in a tree format, just to confirm that the sources list D directory is currently empty. Now, we're going to create a new file in this directory to specify the path to our repository. We need to create this file as the root user because we're working in a system directory. We open the nano editor and first navigate to our sources list D folder, then name the file. Let's call it vbox.list. It's common to use that extension for repository lists. Now we press enter. Let's head back to the official VirtualBox website. Now we need to copy a specific line into the Nano text editor. There's just one thing to keep in mind. We need to replace the section marked as my dist in angle brackets with the actual codename of the distribution. For Ubuntu 22, that codename is Jammy. If you're wondering how to find out the actual codename of your distribution, we'll check it out using one of the terminal commands. Alright, let's copy the text, return to the terminal, and paste it in. So now we have that long line. Instead of my dist in angle brackets, we'll type Jammy. That's the code name for our distribution. So now we have our long line ready. Press Ctrl O to save it and Ctrl X to exit. You can take a look using the tree utility to see if a new file has appeared in our sources list D folder. You can also show the contents of that file on the screen. For example, using the cat command to make sure everything looks good and that we've added a new repository. And don't forget to add the key for this repository. You can do that using the command provided on the website. Just copy it and paste it into your terminal in Linux. Hit enter. The repository key is always public information, so you can grab it from the official site. So we've added a new repository and its key. And as a result of running this update command, we can also see in the first lines that it's working with our new VirtualBox repository. Awesome! Let's reinstall VirtualBox from scratch. Now we can do this using the standard package manager, apt. So we just type the familiar command sudo apt install and add the name of the package, which is called VirtualBox. Hit enter. It will ask for confirmation, so press Y and then enter. Once again, when we get back to the command input line, VirtualBox will be installed. But this time we did it in a centralized way. From now on, updating and all other tasks with this package can be managed using the standard package manager, either apt or dpkg. Great, VirtualBox is installed. Documentation can be accessed in any convenient way, so everything is working fine. Now, let's discuss a small detail regarding the codename of the distribution. In the case of Ubuntu 22, we used the value Jammy. To find out the code name for your distribution, you can type the command lsb release-a. The last line of its output will give us the code name for the distribution, which we used in the repository path for VirtualBox. To sum up our discussion about adding a new repository, if we need to add a new repository, we first write the corresponding line in the sources list file. After this, we add the repository key. By the way, the repository itself, given its HTTP path, is just a regular folder with files. In particular, we can go into it and take a look. Everything is visible. There's another option for adding a new distribution. This one involves using the tool add apt repository. That's its name. If you check the help for this tool, you can find an example of how to use it. Overall, it's pretty straightforward to use. You just specify the tool name and the path to your repository. This add apt repository tool will do the same thing that we just did together. If the add apt repository tool isn't available to you, you can install it from a package called Software Properties Common. Once you install this package, the add apt repository tool will definitely be on your machine. In this section, we're going to talk about a service that lets you schedule tasks. This service is called cron. Along with that, it has a utility known as cron tab. This utility allows you to manage user tasks. The cron service comes pre-installed with Linux, so there's no need to install it yourself. However, you might want to check the status of this service to ensure it's currently running. You can do this using the command system ctl status cron. And look, we can see that the cron service is running on our machine, so we can work with it. If it weren't running, we could start it with the command sudo systemctl start cron. Let's start with managing user tasks. That's where the cron tab utility comes into play. Let's call up the help info for it and discuss the main options, as usual. So, the -e option, short for edit, allows you to edit user tasks. The -l option, short for list, lets you view user tasks. The -r option, short for remove, deletes user tasks. Lastly, the -i option is used for deleting tasks interactively. Now, let's run cron with the -l option to see our user tasks, and we'll find that we currently don't have any tasks listed. Alright, then let's create some. We'll launch cron tab with the -e option for editing. Since this is our first time running this command, we're prompted to choose an editor to use going forward. We need to enter a number, 1 for nano, 2 for vim, and so on. We'll choose the nano editor. Let's type 1. Hit enter and we get a file opened up. Here, we see some text describing the cron service. There's even an example task included. But we'll delete all of that now and write our own tasks. Since we're in the nano editor, we know the shortcut to delete text. It's Ctrl-K. Specifically, this shortcut cuts the text. So we'll systematically delete everything we have in there and write our own. Our first task will look like this. We write 5 asterisks separated by spaces. This format is how we set the schedule for our task. Then we write the command we want to execute according to this schedule. Let's say we want to use the echo command to send some text to a file. We'll write the text "what's the time?" and include the date and time, along with some additional phrase like "it's Linux time." And we'll make sure this text goes into a file located in our home directory, naming that file cron logs. Great! Let's save and exit. Now, if we run cron tab with the -l option again, we'll see the task we just added. Let's go back into editing mode by running cron tab with the -e option, and we can add new information to our task list. We'll add a prompt at the beginning of the text, explaining the syntax used for scheduling. The general idea is that we write one command on each line that we want executed according to a specific schedule. Now let's discuss the format for scheduling those tasks. We have the option to set the schedule in 5 parts: minutes, hours, days of the month, months themselves, and days of the week. In our case, in our example, we used 5 asterisks. An asterisk means that any value is acceptable. So, the task we wrote is the only active one here, and it will run at maximum frequency. For the cron service, that frequency is once a minute. You can't schedule a task more frequently than that with cron. This is simply how cron operates. The cron service pulls all the files where our tasks are stored once a minute and checks the schedule for each task. If the schedule matches the current time, then the command set for that schedule will run. So our command will be executed every time, meaning once a minute. Keep in mind that for minutes, we use values from 0 to 59. For hours, we can specify values from 0 to 23. For the day of the month, we'll use numbers from 1 to 31. And for months, we can use either numbers from 1 to 12 or the first 3 letters of the month's English name, like January, February, March, April, and so on. For the days of the week, we can specify either a numeric value from 0 to 7, where Sunday counts as both 0 and 7. This is because in different countries, the week starts or ends with Sunday. To make it convenient for everyone, that's how it's set up. We can also specify the day of the week using the first 3 letters of its English name. Additionally, we can mention the username between the schedule and the command itself. Now, let's save and exit and return to the terminal. So, we created a scheduled task in cron that will run once a minute. In fact, we created it over a minute ago. So, it has likely already executed something. Let's check it out. We'll take a look at the contents of our folder and see a file named cronlogs, which is where some information should be sent from our task. Let's peek into that file, and we'll notice that there are already 2 lines there. In those lines, we find the exact text that we wrote in the cron task. There's a question about the time and an answer with the current time. If we look closely, we can see that the execution time for this task is 2 hours and 0 minutes. The next execution will be at 2 hours and 1 minute. We can check the current time. And indeed, we'll see that value right here. If we wait a minute and run the command date again, we'll see a different time. Let's take another look at our cronlogs file, and we'll find a new line there. So it really does add a new line to this file once a minute, because our task in cron executes every minute. To make it easier for you to understand scheduling in cron, I'll show you an online simulator. On the website crontab.guru, you can practice setting up schedules. On the page that opens, we see a single text box where we'll be doing our practice. There's also a button on the right above the text box labeled Random. It allows you to generate a random but still valid schedule for tasks in cron. A few examples are provided here. Above the text box, there's a button called Next. If you click it, you'll see the next 5 time slots when the task will run according to the current schedule. These are hints for us. Below the text box, there are hints about each piece of time. Minutes, hours, days, months, and days of the week. Further down, there are hints about the syntax. For example, an asterisk means any value is acceptable. A comma suggests you're listing items. A dash lets you specify a range of values. A slash defines a step. There are also different tokens. At yearly means once a year. At annually is the same as once a year. At monthly means once a month. At weekly means once a week. At daily means once a day. At hourly means once an hour. At reboot, this runs right after a reboot. Using the example schedule shown here, a task will run at 4:05 a.m. every day of any month on any day of the week. And above the text box, we can see hints. For instance, the next time this task will run is on November 21 at 4:05. Then on November 22 at 4:05, November 23 at the same time, November 24, and so on. Once a day at that specified time, the task will run under this schedule. Let's find another example using a dash. So, under this schedule, the task will run as follows. At 0 minutes, 4 hours, which means exactly at 4 a.m. on the days from the 8th to the 14th. The month doesn't matter, nor does the day of the week. Looking at the time, we see that indeed, the first time the task will run is on the 8th at 4 a.m., then the 9th at the same time, the 10th, 11th, 12th, and so until the 14th. Then we wait for the 8th of the next month. Here's another example of a schedule with a comma. So under this schedule, the task will run exactly at midnight, meaning at 0 hours and 0 minutes on the days 1 or 15. They're listed with a comma, no spaces. If there were a space, the syntax would be incorrect and the task wouldn't run. However, between time parts, there must be a space. If we remove the space between minutes and hours, the syntax will also be incorrect and the task won't run. In this case, we can also see that Wednesday is specified in the days of the week, so that condition must be met as well. Tokens like @weekly. This is a handy tip, as it allows the task to run once a week. We see this reflected in the timed examples as well. Let's scroll down to another example where the token sun is used in the days of the week, which is short for Sunday. So, this way you can specify the day of the week, representing, for instance, Sunday. Let's look at another example that uses a slash in the schedule. For example, here in the months, an */2 is set, meaning every second month. The minute is set to 0. In the hours, we have 0, 12, which means at 0 hours and at 12 hours. This way, we get both noon and midnight. The day of the month is the first, every second month, as we discussed, and the day of the week doesn't matter. So, we've reviewed possible syntax options for describing tasks. Also, at the bottom of the page, there's a link for examples. If we click on that, it will show us typical examples of how to set up a schedule. You can click on it to see what's written there. Here are a couple of notes regarding the scheduling format. In minutes, values can range from 0 to 59. So, the 60th minute is an error. Similarly, for hours, we can specify values from 0 to 23. 24 hours is an error. It's also worth mentioning that experienced admins, system admins, and other DevOps folks recommend avoiding the 0-minute in scheduled tasks, because during those times, there's a chance of peak load on the servers, even without our task. As a result, it may happen that our task will be executed with some delay, and if the execution time of the task is critically important for us, then it's better to choose a minute further away from 0. You could even select the 59th minute, just to give a little buffer. Let's get back to the terminal and take a quick look under the hood of the cron service. For instance, if you open a file located at this path, /var/spool/cron/crontabs, and the file named after our user, itguy. Of course, you'll need to open it with root privileges. And surprise, what do we see here? A list of our tasks that we've written down. This tells us that all task lists, like all settings in Linux, are stored in simple text files. But if we try to navigate to the crontabs folder, we won't be able to, even with the sudo prefix. To access it, we first need to switch to root mode by using the command sudo su, and then we can try to enter that crontabs folder. Once we do that, we will indeed find the itguy file, which contains the tasks for the itguy user. We can display the contents of this file again to verify it. Now, let's return to regular user mode with the exit command and check that crontab-l gives us the same content we just saw in that file. At this point, a tempting idea might pop into our heads to edit our tasks by opening this file. But right now, I want to show you why that idea is flawed. Watch this. Let's open crontab with the -e option to edit our tasks. Now, let's imagine a scenario where, while editing a task, we make a syntax error. For example, in one task, we forget to insert a space between two time segments. In another task, we set the hour to 24, which is also unacceptable. And a third time, we mess up again and specify 4 time segments instead of 5. As a result, we have tasks with incorrect schedules. Let's assume we didn't notice these mistakes. After saving and exiting, look at what happens next. We get alerted that there are errors in the crontab file. It asks us if we're sure we want to save these changes. We can press yes, the Y key, to save, or no, N, to discard our changes. We'll choose no to avoid saving those changes. Then we can check, and indeed, our changes haven't been applied. But don't worry, our changes were safely saved in a backup file. You can open that backup file at this path, check it out, and see that it contains the text we left at the end. However, this text does not represent the schedule for our active tasks. So we've confirmed that the crontab utility performs certain checks before saving our tasks to avoid syntax errors in schedule creation. This makes it a safer way to set up task schedules, and those checks wouldn't have happened if we had edited the file directly. That's why I emphasized that it's safer to use specialized utilities instead of directly editing configuration files. Now, let's discuss how the operating system interacts with the cron service. For example, if we take a peek into the crontab file located in the /etc directory, we will see some tasks. We didn't add those tasks ourselves, yet they are present there. So, these are system tasks. That means we can also add tasks to this file. I didn't say it was prohibited, but it does mean taking on more responsibility. Because if we make a mistake in the syntax for creating a schedule, there won't be any automatic checks to catch it. And the problem isn't just that our task won't run. The scary thing that could happen is that the entire cron service might crash. In this task list, in this file, It's also standard to specify the username under which the task will run. In this case, we have examples using the root user. That works as well. Let's talk about setting up logs in the cron service. How can we work with cron logs? We can do it in a rough way. For example, we could use the grep command to search for the word cron in the system logs file, which is located at /var/log/syslog. By doing something like that, we will surely find something. But that's a messy way to handle cron logs. There's a more sensible option. Specifically, we can edit the system log service file to configure the cron service to send its logs to a separate file. So, let's edit the settings. We look for the line that starts with the word cron. In this case, it's commented out with a hash symbol. We'll uncomment it and then write the path to the file where we want to store cron logs. We save it and exit. After that, in order for our changes to take effect, we need to restart the system log service. It's called rsyslog. We can do this with the command sudo systemctl restart rsyslog. And we'll also restart the cron service. Sudo systemctl restart cron. Let's take another look at our settings file to remember the path we set for the cron logs. We'll copy that path. Now we can check the file at that path. And we see that it already has a few lines. In a minute, our task will run again, adding a new line to our log file. And this line will also appear in that file. It will show that our command continues to run once a minute. By the way, we can peek at our log file where we're adding entries every minute and confirm that a new line is still being added there every minute. To stop this task, we either need to stop the entire cron service, clear the task list, delete this task, or the easiest option, just comment it out. Let's save it and exit. We can check to verify that we currently have no active tasks. Everything that's written here from crontab-l is commented out. Each line is preceded by a hash, so all these lines are inactive. Now, let's talk about deleting user tasks. In the crontab help, there was the -r key. Let's see how it works. First, let's output our current list of tasks and run crontab-r. After that, our user has no more tasks. We can check. Yep, they've all been deleted. We can also take a look in that file where we saw our tasks. First, we switch to the sudo su command. Then we'll navigate to the crontabs folder to check if that file is gone, since we've cleared the task list. Next, we'll return to our user with the exit command. Now, let's discuss one last feature of the crontab utility, which is managing the tasks of another user. This is done using the -u option. In other words, you can type crontab-u followed by another user's name, such as sales guy, and -l to see that user's tasks. However, if you try to run that command in this way now, you'll encounter an error message because you need root permissions to view and manage another user's tasks. So, in the previous command, you'd have to add the sudo prefix. If you have the ability to execute commands with this prefix, you'll be able to see the tasks of the sales guy user. In this case, he has no task, and our current user, IT guy, also doesn't have any tasks because we just deleted them. So, let's get our previous tasks back by editing the cron tab with the -e option. We'll paste from the clipboard, remove any unnecessary items, restore the previous tasks, and save it. Let's check it. Great! Now we've restored the previous task list for our user, IT guy. Next, we can log in as another user. Let's say, switch user sales guy. We'll log in as him. Let's check and make sure we're currently working as the sales guy user. Now, let's run his cron tab, for example with the -l option to verify that he currently has no tasks. Next, we'll add some tasks for him. We'll type crontab-e. Since this is our first time doing this, we'll be prompted to choose an editor. For simplicity, let's select Nano. Hit Enter. In this editor, we will remove the unnecessary lines using Ctrl-K to cut a line. We'll keep a few lines. Here's a task example. We'll duplicate it a few times and uncomment it, leaving it in this form. Now we'll save and exit, then check the Cron tab with the -L option in the terminal. Now, the user sales guy has several sample tasks. Let's exit and return to our main user, IT guy. Now we can see that running cron tab -L shows the tasks of the user we're currently logged in as. So, returning to the topic of managing cron tasks for another user, we'll type sudo cron tab -u sales guy -L. Let's check the tasks for the sales guy user. And there they are. Great! What's more, we can not only view but also edit and even delete them. Let's start with the -E option. We might be asked to choose an editor again. Let's take Nano, hit enter. We can modify those tasks as we see fit, maybe even remove some unnecessary ones. We'll save and exit. Now checking the tasks of our sales guy user again with cron tab -L. Indeed, they are in the form that we saved them last time. We can even delete another user's tasks by using the -R option. Hit enter. All done. The sales guy has no more tasks. If we run cron tab with the -L option for our current user, everything remains unchanged there. That old task list for the user IT guy is right here. To check, we can switch to the user sales guy. Just do switch user sales guy, enter his password, and take a look at the task list. And we see that, yes, indeed, the user sales guy still has no tasks. So, in this section, we discussed task management based on a schedule. We talked about the cron service, the cron tab utility, and setting up logs. In this section, we're going to talk about how the firewall works in Linux. Of course, Linux comes with a built-in firewall called NetFilter. The utility used to interact with it by default is IP tables. If you hop onto the short help section for the IP tables utility, it basically tells us that it's an administrative tool for filtering traffic. The number 8 in the help text indicates that it's an administrative utility. When you see the number 1, it usually refers to user programs. Generally, IP tables is included with most distributions right out of the box. But if you find that it's not installed, you can get it with the command sudo apt install IP tables. In its simplest usage, you can type sudo IP tables -L. The L stands for list, meaning it will show you the current list of rules in that utility. What's important here is that you always use the sudo prefix when calling IP tables. As we mentioned, this utility is administrative. To better understand the information it provides, let's visualize this a bit. Let's remember what a firewall does. So we need a firewall when we decide to protect our precious machine from the outside world. For various reasons, we consider the external world to pose some level of danger to us, and we want to manually manage how our machine interacts with that outside world. This includes allowing certain things, blocking others, and taking additional actions as needed. The interaction between the machine and the outside world is all based on requests. Requests come in different types. For example, there are incoming requests, meaning they're coming from the outside world to our machine. Then there are outgoing requests, which are from our machine to the outside world. Lastly, we have transit requests. These are from the outside world, through our machine to somewhere else in the outside world. For each of these request types, we create chains of rules. These chains have their own names. For instance, the input chain has rules for incoming requests. The forward chain holds rules for transit requests. The output chain contains rules for outgoing requests. All of this can be seen by typing sudo iptables -L. In this case, it will show us all 3 main chains. We can see that currently, there are no rules in these chains, just the headers. The firewall works like this. Whenever a request tries to execute, the firewall checks it against the relevant chain of rules first. As soon as it finds the closest matching rule, it gets applied. If there's no suitable rule in the chain for a particular request, then a default policy applies to that request. In our example, we see that the policy everywhere is set to accept, meaning allow or take in. You can also write rules for pre-processing and post-processing requests. Let's write a few examples of how we can add a new rule in the iptables utility. For instance, let's say we want to log all incoming requests. So, to set this up, we start by typing sudo iptables, followed by the option -a, capital A, which stands for append, meaning we're adding a rule. Next, we specify the chain we're adding to. Let's choose input for incoming requests. Then with the option -j, we indicate what action we want to take. We'll select log because we want to log these requests. Now, we can check our list of rules using the option -l. We'll see that a new rule has been added to the input chain. So we are logging all the incoming requests. To see if our new rule is working, we'll send a ping request to our Linux machine from somewhere outside, which means an incoming request. Let's recall our IP address using the command hostname -i. Now let's take a look at the log file. We can use the tail command for this. The log file is located in /var/log/syslog. Now, let's run the tail command with the -f option to monitor the file in real time. We remember this option, F, from our earlier lessons. It's clear that the logs are streaming in. Everything is functioning as expected. Next, we'll switch to the Windows terminal and send simple ping requests to our Linux machine. We'll notice that while sending these requests, new lines appear in the Linux logs. Here are our ping requests, and corresponding lines just showed up in the log window. You can confirm this by checking the IP address. We can also clear the list of rules. To do that, we use the uppercase option -f, which means flush. Executing sudo iptables -f will clear all three chains. If we specify a chain, like input, output, or forward, it will mean that we are removing all rules only from the specified chain. After clearing the rules, we can check again with -l and see that now we have no rules at all. For variety, let's add logging rules to all three chains. We want to log in the input chain. We want logs to be written in the output chain, and we'll also log forward requests. Let's check this. Now we can see that 3 new rules have appeared, one in each chain. Let's practice adding new rules some more. First, we'll check the IP address of our machine in Windows. In the Windows terminal, we type the command ipconfig and see the network interface information. What we need right now is the line with the number 192.168.0.100. This is the IP address of my Windows machine in my local network. Now, in the IP tables, we'll write a rule to block requests from the Windows machine. So, we type the command like this, sudo iptables -a, which means we're adding a rule to the input chain, and with the option -s, we specify the IP address. Let's insert it here, 192.168.0.100 in our case. Next, with the option -j, we indicate the action we want. Last time, we used log to log requests. This time, we'll write drop, which means to reject or discard. Using the L option, we check the updated list of rules and see a new drop rule. So, we are dropping all requests from the specified IP address. If the rule is here, that means it's already in effect. Now, we'll no longer be receiving requests from the Windows machine. Let's head back to the Windows terminal and try sending a simple ping request to our Linux machine. We'll ping the address 192.168.0.102. So we've got machine 102 running Linux and machine 100 running Windows. And we're noticing that the requests are timing out and just not getting through. We can see a corresponding message in the results. When we check the list of rules using the -l key, We can also add another option, which is dash line numbers. This will show us the sequential number for each rule. Having the rule number can be handy if we want to remove a specific rule based on its number. To do this, we'll use the capital -D key. The command for deleting a rule will look something like this. We'll type sudo iptables -d, then specify the chain, for example, input, and then the number of the rule we want to delete. Let's say that's rule number 2. With this command, we remove the second rule in the input chain. After checking, we see that the drop rule is no longer there. That means our ping requests and any other requests from the Windows machine should work again. We can check this in the Windows terminal. We send some simple ping requests again, and voila, they go through and we get responses. Apart from the drop rule that blocks requests, there's also the reject rule. This also blocks requests, but it works a bit differently. Let's look at an example. We'll repeat our rule that was blocking requests, but this time instead of drop, we'll write reject. Hit enter. Now let's check the list of rules. We can see that a reject rule has been added. It's still blocking those same requests from the Windows machine. Now, let's see how our simple ping requests go through. So again, in Windows, we'll ping the Linux machine. What do we see? We see that the requests are going out, and we're getting responses, but the response tells us that the destination port is unreachable. In other words, it's like a polite, refined way of saying no. This highlights the difference between the drop and reject rules. When we had the drop rule, the target Linux server didn't respond at all. It was as if there was no machine with that address. But when the reject rule is in effect, the machine responds. But it responds with a refusal. The reject rule is a more polite way to decline. However, it's also a bit more resource intensive in a sense. That's because it involves sending a response packet back. In contrast, the drop rule just ignores the requests altogether. They're not processed in any way, simply discarded. Currently, we have incoming requests from a Windows machine blocked due to the reject rule in place. If we want to allow requests from this machine, we can specify an accept rule instead. Basically, we just repeat the previous rule, but swap reject for accept. Now, we can see a new rule allowing incoming requests from the machine with the IP address 192.168.0.100. It seems like we've allowed it. So, we're in a bit of a to execute or to pardon scenario here. Before we check which of these rules is actually being enforced, I want you to think about this question for a moment. Then we can discuss it together. Let's head over to the Windows terminal, send some ping requests again, and we'll see that these requests aren't going through. We're being blocked. Clearly, the reject rule is in effect. But why is that? It's simply because it's positioned above the accept rule. When we sketched out how the iptables utility works, we mentioned that the firewall goes through its chain of rules for requests. As soon as it finds the first applicable rule for that request, it applies that rule. What's lower down the chain doesn't matter at all. So, the order of rules in iptables is very important. Typically, we place stricter rules at the top and more general rules below. In a way, the most general behavior rule is the default policy, which we currently have set to accept. This means we're allowing everything by default. To illustrate this better, we can add the NV flags to the iptables output. This adds a column showing the number of packets. Now we can see that packets were flowing through the reject rule, but there were 0 packets passing through the accept rule. We can run a few more ping requests and check again to see which rule is receiving packets. Once again, we see that it's the reject rule. So, the reject rule is working while the accept rule is ignored. It never even gets a chance to be reached. When we work with the iptables utility, we do this as the root user. In other words, we prefix all commands with sudo. That being said, it's convenient to switch to root mode with the command sudo su. This way, we won't have to prepend sudo to every single command. In previous examples, we added a new rule using the -a option, which stands for append. This option adds the rule to the end of the chain. But it's also possible to add a rule to the beginning of the chain using the -i option, which means insert. Here's an example. We type IP tables, -i, followed by the relevant chain. Let's add a rule to the input chain. We'll specify a random IP address. And what are we doing? We use -j option and then drop. Now let's check the list of rules. We can see our new rule has indeed been added to the start of our chain. Additionally, if we use the I flag, we can specify the line number at which we want to insert the rule. For instance, if we type line number 3 and specify an IP address, hit enter, and then verify, we'll see that our last rule was added in the third position. This is possible with the key -i. To remove the rule we need, we say IP tables -d, which means delete. Next, we specify the chain from which we're deleting the rule and the number of the rule to be removed. Let's say this will be the third rule. We check and see that the number of rules is now one less. The previous third rule is gone. Now let's work with the output chain, which contains rules for outgoing requests. So, what are outgoing requests? These are requests coming from our machine directed to the outside world. For example, browser requests. If we open our browser now and head to a website, that would be an outgoing request. Now, let's go back to the terminal and write a new rule that will block our outgoing requests by default. We write IP tables -a, which means append, to add a rule to the output chain, -j drop. So we are rejecting or blocking all outgoing requests. As we can see, a new rule has appeared. Since it's now in the chain, it's working already, and we won't be able to access any websites anymore. Next, let's talk about default policies. This is the action that will be taken when no suitable rule is found for a request. As an example, let's set the policy for the input chain to drop. For this, we write the command IP tables -p with P standing for policy, input chain, and the rule drop. Let's check. Now we can see that instead of accept, the policy is set to drop. This means that incoming requests are denied by default, except for those with rules that allow them in this chain. If we now do a simple ping request from a Windows machine, we'll see that the response looks the same as with the reject rule. That's because we currently have a reject rule that triggers before the default policy is applied. So, to make things clearer, let's remove the reject rule. The reject rule is on line 3, so we'll remove rule 3. IP tables -d input 3. We see that this rule is gone. Now for the Windows machine, the accept rule is functioning. It will obviously allow requests. But we want to demonstrate the default policy, so we'll remove the accept rule as well. This rule is also now number 3. So we remove the rule number 3 from the input chain once again. Now let's see how the ping requests will go through. And here, we see that requests are timing out, because that's exactly how the drop rule works. In this case, the policy is drop. This is a situation where the target machine doesn't respond to requests at all. We can also add an exception allowing rule for our Windows machine. IP tables -a input, the IP address of our Windows machine, and -j accept, to allow requests from machine number 100. Let's check and see that requests are now sent successfully and returned with responses. Up to now, we've been writing rules for IP addresses, but we can also set rules for port numbers. Let's consider an example. First, we're going to remove our allowing rule for the Windows machine, and instead, we're going to create a new allowing rule for port number 22. As we know, port number 22 is used for SSH protocol connections, so let's see how this will affect things. Alright, let's write the new rule. You start with IP tables -i, which means insert in the input chain. Next, we need to specify the key -p and the value TCP. Then we use the key --d port and set the destination port to 22. We're setting a rule for port number 22, and with the key -j, we allow it. Accept. Let's check. We can see that our first rule is to allow incoming requests that are sent through port number 22. Now let's try running our favorite ping request. But we see that it's not going through because actually the default policy is set to drop. Our allowing rule pertains to port number 22. And if we try to connect to this machine using the SSH protocol right now, we should be able to do it. Let's give it a shot. We type in the Windows terminal the connection string, SSH, space, username, @ and the IP address of the machine. We'll be prompted to enter the password, so we type it in and hit enter. And here we are on the Linux machine. Even though the terminal window on Windows is open on our host machine, we can now manage our Windows server from here. We can type in some commands like who am I, or check the state of IP tables to see what rules we have in place, and so on. Everything is working. That's because we allowed SSH connections, which use port 22. Now I have another piece of news for you. Guess what will happen to all the rules we wrote in IP tables when we reboot our Linux server? Of course, they won't be saved. They will be removed. This is done for security reasons, so that first of all, they aren't stored in any text file, and secondly, to ensure we can regain access in case we accidentally lock ourselves out. If we set some restrictions and can't connect afterward, we need tools to save the list of rules and then restore them in IP tables after a reboot. Tools like IP tables save and IP tables restore can be used for saving and restoring rules, respectively. Let's see how they work. So, IP table save is, of course, an administrative utility. If we're operating as a regular user, we'll need to prepend it with the prefix sudo. So we type IP table save, followed by an arrow pointing right. We say we want to send the output of this utility to a file, which we can call something like IP tables rules. Hit enter. Now we see that we have a file called IP tables rules. It's a text file, and we can take a look at it. And that's what we're going to do now. Next, we'll reboot our Linux server. After the reboot, we open the terminal again and make sure that there are no rules left in the IP tables utility. But the file has been saved. Let's check it out. We'll output the contents of the IP tables rules file, for example, using the cat command, and then we can discuss what's inside. In the first line, it's commented out for us behind the grid. We mention the version of the utility IP table save and the date this backup was created. Then, after the asterisk, we note the filter table. This is the main table that we've been working with today. Next, we list the names of the chains and the default policies that are set. For input, it's set to drop. For forward, it's accept. And for output, it's also accept. After that, we see our rules in the input, forward, and output chains. Below, there's a description of the behavior in the not table, but we haven't discussed that yet. So, great job to us for saving the list of rules in a text file ahead of time. Now, we need to restore these rules from this file into IP tables. We do this using the command IP tables restore. So, we write sudo IP tables restore. We specify that we're providing our file, IP tables rules, as input to this utility. Hit enter. Now, we check the list of rules and see that our rules have been applied again. They have been restored to their respective chains. Now, they are working again. In this section, we discuss the IP tables utility, which allows us to manage the Linux firewall. Specifically, we talked about the capabilities for editing rules, adding, removing, and displaying the list. We also cover the default policies and tools for saving and restoring the list of rules. So, what exactly is Bash? Let's take a quick historical detour. In the early days of Linux, a shell called sh emerged. Its name stands for shell. This shell was capable of executing some commands and was received quite warmly by users. There were also high expectations around the sh shell from the users. However, it didn't really evolve for a while. Then, as often happens, another programmer came along, rewrote the existing functions of the sh shell, and named his new shell bash. Bash is named as a nod to the original shell, as it can be interpreted as born again shell. Interestingly, the word born is a pun, referencing the last name of the shell's developer, while also sounding like the word born. So, bash is a command interpreter, our shell. It's the environment that users log into, defining the set of commands they can execute. As of today, bash is the most popular shell in Linux. It's also the shell we've been working with throughout this course. Moreover, bash functions as an entire programming language. It's an older, fairly simple scripting language, and today we are going to get familiar with its basics. We will write our first script. Most programming typically starts with displaying the string hello world. So let's go ahead and create a hello world script in bash. We'll create our first script in the Vim editor. Hello world.sh. Bash scripts usually have the sh extension. Remember that in the Vim editor, to start editing text, you need to switch to insert mode. To do this, press the I key, which means insert. Now we are in insert mode and can start writing our code. The first line we write will look like this. It's a hash symbol, an exclamation mark, followed by /bin/bash. This indicates the path on our machine. So on this server in the root of the file system, there is a folder called bin, and inside it, there is a file called bash. This file is the interpreter for the code we will write next. In other words, the code in this script will be passed to the interpreter via the path /bin/bash. To keep it simple, we'll write a straightforward command, echo hello world. Next, I'll add a hash symbol and some extra text. Great! We've written our first script. Now we need to save and exit. While in insert mode, we need to switch back to command mode by pressing the escape key. Then we type in our command. Of course, you remember this command from previous lessons. It's :wq. The W stands for write, meaning to save changes. The Q stands for quit, meaning to exit. So, save and exit. Press enter. Perfect. As you can see, our script has been created. Now let's display its content on the screen. For example, using the cat command. And to run our script, we can explicitly call the bash interpreter and pass the file name as a parameter. Press enter. So we see that the echo command is executed and outputs our beloved hello world. And notice that it only printed the line hello world. The text after the hash, like aloha, ciao, didn't show up. That's because we know that the hash symbol indicates a comment in many programming languages, not just in bash. In other words, any text following the hash until the end of the line is ignored by the machine. This part is just an explanation for us humans. Let's open our file again and add a few more lines of code. In Vim, we'll switch to edit mode by pressing the I key, which stands for insert. Now, let's output the next line using the echo command again. We'll type who am I. Let's say we want to display the name of our user, and we want it to be determined automatically. For this, we have a system variable called user. So we write $user. The dollar symbol is used to refer to the variable for reading. And the user here is written in uppercase. That's because that's the specific variable that exists. It's an environment variable. On the next line, let's show our current location. We'll say where am I? And to find out the current folder we're in, we can use the command pwd. Remember, pwd stands for print working directory. So pwd is a command, not a variable. To make it execute here and return the result in text form, we need to format it like this. We write $, then our command in parentheses. That's how we leave it. Next, let's output the name of our operating system. We can get that from the command uname. Since uname is a command too, we'll wrap it in parentheses and put a $sign in front. Now, let's also show the home directory of our user. We can retrieve that from the variable home. So we write $home without any parentheses. Variables don't require parentheses when we're accessing them. Great! To save our changes, we first exit to command mode by pressing the escape key. Then we type :W to save, and then :Q to quit. Now let's display the contents of our script on the screen, and we can see that all the new lines have appeared. Let's run it one more time. We type bash, the name of the file, and hit enter. Awesome! All commands are executed, all text is printed, and everything is working perfectly. But usually, when we run scripts, we don't refer to our interpreter so explicitly. We typically just write the path to the file, and that runs the script. However, for that to work, the script file must have execute permissions. As we can see, files don't automatically get execution rights right after they're created. But we know the command that grants permissions. Can you recall it on your own? Let's type it together now. So, it's change mode, or chmod, and we say user plus execute, which means adding execute permission for the owner, and then we put the name of the file. Hit enter. Let's check. We can see that the letter X appeared in the owner's permissions. This means our user, IT guy, who owns the file, can now execute this script. But if we just type the file name and hit enter, we'll only get an error message. So, what happened? The thing is, to run a script, you need to provide the path to the file, not just its name. For example, you start with a dot. That is, // followed by the file name. In this format, the script will execute. Alternatively, we can write the absolute path to the file, starting with a slash, like /home, /itguy, all our folders, file name, enter. That will work too. Or you can write the path starting with a tilde, which points to the home directory, where our file is located. Remember this, it's an important point. To run a script, we write the path to the file, not just its name. Now, let's say a few more words about that first line we started with, which has the hash and exclamation mark symbols. It's called the shebang line. This line indicates the path to the interpreter that will execute our script. We wrote /bin/bash here, but we're not always required to use this specific path or this interpreter. In the first line, the shebang line, we can specify the path to any interpreter that's available on our machine. Let's give an example. Let's create another file. In the shebang line now, I'll write hash symbol, exclamation mark, and then the path /user, /bin, /python3. What, as you can guess, will allow me to write code in Python. Let's insert some random code here. We save it and exit. We have a new little script now, which we named myCalendarPy. To make it easy to run the script, we'll give it execute permissions using change mode, user plus execute for our file. We'll check to ensure that the appropriate permissions have been granted to the owner, display this on the screen, and send it to execute. Great, we see that our Python code has executed successfully. So, what happened? Let's break it down. When we sent our file to execute, the terminal, our shell, read the contents of our script, noticed the shebang instruction in the first line that indicated who should run this code. And accordingly, it passed our Python code to the specified interpreter, and Python executed what was written there without any issues. You might reasonably ask, what do I do if I don't know where the interpreter is located? And really, how can I tell if a particular interpreter is installed on my machine, whether it's Python, PHP, or something else? To answer that question, we have the command whereis, so we can type whereis bash. and it will show us the path where the bash interpreter is installed. Or where is Python 3, one of the examples we just used. Or where is Perl? This way, we can see that the Perl interpreter is also available on this machine. If we type where is PHP, we'll find out that no, PHP is not installed here right now. Or Ruby 2, it's not installed. In one of the earlier sections of our course, we learned how to create users. Using the command user_add, we came up with a username and created it with the -s option, usually specifying /bin/bash. So, what we meant by that is that the user will be set up with the bin bash shell. You can take a look at the file path wd in the etc. directory to confirm that our users have been assigned the bin bash shell. That's because it's the most popular shell out there in Linux these days. The shell determines the commands that will be available to the user. It's essentially the working environment where they operate. Also, remember that if you see no login or /bin/false next to a user shell, that typically indicates we're dealing with a daemon. This is a system account that can't log in and is only meant for running services. It's worth mentioning that bash isn't the only shell available in Linux. So, how can you find out? Perhaps I'm not using bash right now. Maybe I'm working in a different shell? You can check the current shell in several ways. The simplest option is the command ps. If you run it without extra parameters, it will show you information about the current process. And there you can see it. It's a bash terminal. You can also use various environment variables. Let's use the command echo to display the variable $0. It holds the name of the current shell. Another variable is shell. It contains the path to our current interpreter. Just remember to write shell in uppercase. You can view the list of shells available on your machine in the file /etc/shells. There, you'll see that there is the sh shell or bash shell that we're working in, and some other shells that are also present on our machine. For those in the course who are using Mac OS, you might know that the default shell there is called ZSH, and the name kind of hints at the similarities among shells. We also remember that Linux and Mac OS were born in the same environment, having a common ancestor, which is the Unix operating system. That's why the shells are also named similarly. Many of the commands that work in the Linux terminal can also be successfully executed in the Mac OS terminal. This is simply because Mac OS and Linux are two related operating systems with similar approaches to managing machines. Let's start our chat about Docker. This tool is incredibly popular and important, yet it's quite simple to use. First, let's check if we have it installed. We can try calling for help with the command docker --help. It turns out that in our case, on Linux Ubuntu, it doesn't come installed by default. But don't worry, installing it shouldn't be complicated at all. We've got a couple of installation options, either through snap or apt. So we can just copy one of the suggested commands. You can do that easily with Ctrl+Shift+C and then Ctrl+Shift+V. The package we want to install is called docker.io, at least in the apt package manager. It's also a good idea to add the -y flag at the end of the command. That way, we won't be prompted for anything during the installation. By the way, we covered lessons about package management and software management in Linux, including the apt and snap package managers, in the basic Linux course. So let's execute our command. If it asks for a password, just type it in. Alright, here we go. In just a few seconds, Docker will be installed, and we'll get our command line back. We'll run the help command again to confirm that it's installed, and then we can start talking more about it. Fantastic. You can also call a one-liner help command with what is Docker. Yep, it's all there. Now we have Docker on our machine. Before we dive in and start playing with it, let's take a quick historical detour. How did the IT industry come to Docker? How did it evolve in the context of virtualization and containerization tools? So, let's rewind a bit. In the early days of the IT industry, every project would get its own physical server. That means a new project would get a new server, and then another project would get a different server. I'll just write a quick note here. Is RV1 for one server, and SRV2 for another. This setup was necessary, so that each project could run in its own isolated environment without interfering with each other, giving each project its own resources. Easy and straightforward, right? But there are significant costs associated with this approach. No matter how high demand a project is, it will always have peak hours when its resources are heavily used, and then there will be quiet times as well. For instance, I've drawn a load graph. On each server, there will be times when our hardware isn't being actively used, and that's not optimal at all. So, the challenge for IT folks became clear. How can we optimize this situation? The IT professionals brainstormed a bit and came up with a solution. They decided to get a bigger server and run virtual machines on it. Just one virtual machine, another virtual machine, as many as could fit. So, think of a big rectangle representing the server, SRV, which is the host for the virtual machines. The physical machine, SRV, is there, and inside it are the virtual machines, which I'll label as VM1, Virtual Machine 1, and VM2, Virtual Machine 2. Clearly, this approach is more efficient. It allows the shared hardware resources to be used effectively, but then new problems arose. Let's see what those problems are. The server, the physical machine that acts as the host for virtual machines, runs on an operating system. The operating system consumes a certain amount of resources. Next up, each virtual machine also operates on an operating system, which also takes up a specific amount of resources for its functioning. As a result, there's significantly less useful space left. I will highlight it in yellow. So, it turns out that there are also costs associated with the virtual machine approach. Looking at this image, in this example, we launched 3 operating systems for 2 projects. That's quite expensive. Of course, it's better than the initial setup when each project ran on a separate machine, but it's still far from ideal. So, the IT folks got together to brainstorm a bit more and came up with the following idea. Let's take a larger server, similar to how we handle virtual machines. SRV, physical machine, host, and now, instead of launching virtual machines on this server, we're bringing up what are called containers. A container is a significantly lighter entity. I'll just refer to them as C1, C2, C3, C4, and so on. Because containers are much lighter than virtual machines, we can fit more of them on the same hardware. A container doesn't need to be a full-fledged operating system. Thus, we can clearly see resource savings. In summary, you could say that containerization is, in some sense, a specific type of virtualization, essentially a way to run projects on shared hardware resources, but within an isolated environment and with minimal overhead compared to virtualization. And Docker is the specific software that implements this containerization idea. To see the main commands for Docker, you can call up the help by running docker-help. Since we just installed it, the help shows us the basic set of commands. Instead of just reading through these commands, let's sketch them out for a better understanding. So, what do we have at our disposal when we're talking about Docker? We have our wonderful Linux server, the machine we're working on. That's where we just installed Docker. Additionally, somewhere out there in the cloud is something called Docker Hub. I'll just refer to it as DH for short. Docker Hub is a repository for images. Many files are stored in the image registry. These are binary files, hefty files. They can weigh anywhere from megabytes to hundreds of megabytes or even dozens of megabytes. That's perfectly normal. They're just files sitting on a disk. Because of their large sizes, to avoid having too many copies on all machines, they've been moved to a separate Docker hub. You can think of it like packages. Just like we know that all packages in Linux are stored in repositories, we can download them, install them, and set them up on our machines. So, Docker Hub is a similar repository for images. Next up, we have our own commands. For example, to download an image to our machine, we use the letter I, standing for image. To get an image file onto our machine, we need the command pull. Docker pull allows us to download an image to our Linux machine. If we're unsure of the exact name of the image, we can use another command. To find the right image, we use the command search. Docker search lets us look for an image in Docker Hub. Now, why did we download that big binary image file onto our machine? It's so we can run an application from it, which is called a Docker container. I'll mark it with ASC for container. A container, unlike an image, is a running application. The whole infrastructure exists for these containers. So, while an image as a file just takes up disk space, a container as a running application consumes RAM, CPU resources, and so on. By the way, we launch a container with the command run. Docker run lets you start a container from an image. Then, at some point, we decide we no longer need that container and want to delete it. You can do that with the rm command. Docker rm is a command similar to remove when dealing with files and folders. But here's an important detail. You can't delete a running container. You first need to stop it using the docker stop command. So, first docker stop to stop the container, and then docker rm to remove it. That's the default process. If we want to delete an image, the file, we can use the command rmi, short for remove image. In other words, rm deletes the container, while rmi deletes the image. What other commands do we have? For instance, to view the list of images that are on our machine, you can use the docker images command. To check the list of containers, either currently running or all the ones we've ever launched, you can use the command ps, which is docker ps. Now, this isn't a complete list of commands, but these are the basic ones that you'll use most often. If we refer back to the Docker help documentation, you'll see these commands mentioned. There's search for finding images. Then we have pull for downloading them. PS is used to list the containers. Images lets you see the list of images. Run is how you start a container. rm is used to remove a container. rmi is for deleting an image, and so forth. Another handy command we'll need is exec, short for execute. This allows you to run a command inside a container. We'll definitely talk about how and why to do that. We'll also look at the build command, which lets you create a new image from a Docker file, and so on. Now that we have everything set up and know the commands, let's play around with them. For example, let's try docker ps and see what happens. We'll get an error message. Because, you see, Docker is essentially an admin tool, and access to its commands is typically granted under the root user. So by default, we run Docker commands prefixed with sudo. The command ps is supposed to display a list of running containers. But if we look, oh no, there's nothing there. Just the headers and an empty table. This means we have no running containers at the moment. If we add the flag -a to the ps command, it should show us the list of running containers, as well as all other containers we've ever launched, even if they are currently stopped. But that list is also empty. We don't have any containers right now. Let's check the list of images with Docker images, and again, it's empty. Just the headers and no images at all. This makes sense. We just installed Docker and haven't created anything yet. So it's time to launch our very own container. In programming, it seems like everything starts with hello world. And Docker has a hello world container too. Let's go ahead and run it. We use docker run followed by the container name hello world. But Wait a second. What are we going to run? We just checked and we have no images or containers. So right now, when I hit enter, magic is about to happen. And we're going to get to know that magic. Alright. Let's launch the Hello World container. Look at what it tells us. In the first line, it says unable to find image locally. Of course, it can't find the image locally. We didn't have anything. Check out the next line. Pulling from library. From which library? Of course, it's Docker Hub. The next line tells us, pull complete. We've downloaded the Hello World container image. And the text we see next is the output from our container. That is, the Hello World container simply prints out some text with general information about Docker and then finishes its job. How do I know that our container has finished? Because it returned us a command line prompt. So, if I try to check the list of running containers with the command docker ps now, I won't see anything. There are no running containers, not a single one. So, the key -a in the ps command will show us that we actually had one container running from the Hello World image. Right now, it's in an exited state, meaning it has finished its work and unloaded from memory. And what's interesting is, if we look at the list of images, we'll see our Hello World image listed there. So, what happened when we ran the command docker run hello world? Basically, the run command works like this. It first tries to find the image with a specified name on our local machine. If it finds it, a container from that image will be launched. But if Docker can't find an image with that name, it searches in Docker Hub. If it finds the image there, it will be downloaded and a container will be created from it. So, if I run the docker run hello world command again now, notice that nothing gets downloaded. The container starts up immediately from the image that's already on our machine, runs, and then stops right away. It just remains in the command history. So now, in our history of started containers, we have two entries. Both of these containers ran and stopped because the status is exited. Let's talk a bit about the prefix sudo. You see, by default, when we use Docker commands, we do so as the root user. However, there's a way to get around having to type sudo every single time. And of course, Linux has its little quirks. We'll go through what you need to do right now. But if you plan to do this at work, especially on a production server, make sure to consult with your senior colleagues first. In some companies, this action could be seen as lowering security levels. So, to be able to run Docker commands without typing sudo, we need to add the current user to the Docker group. First, let's create a group named Docker as the root user by using the sudo prefix and the command group add, calling the group Docker. Oh, good news! That group already exists. You can check this by looking at the /etc/group file. Yep, there it is. We see the Docker group, and in this case, its number is 136, but there are currently no users in it. No users have been added to this group yet, so we need a command that adds a user to a group. If anyone remembers that command from previous lessons, or knows the command for adding a user to a group, great. If you don't remember, try to recall it on your own first. By the way, there can be different formats for that command. We will use the command user mod, which stands for user modify. The flags are -a, meaning append, and -g, capital G, for the list of additional groups. The group is called Docker. And who are we adding? The current user. You can either specify the user by their login, which in our case is as IT guy, or you can use a more general format like $user. Make sure to use user in all caps, because it's an environment variable that holds the current user's name. Hit enter. Awesome. You can take another peek at the etc group file and see that the user IT guy is now in the Docker group. Or you could run the groups command in lowercase, group's username. Yes, Here we also see the Docker group. Now, we either need to restart our Linux server, which is usually not a great idea, especially with important services running, or we can simply restart the Docker service instead. So instead of rebooting the entire machine, we'll just restart the Docker service. The command is sudo systemctl. This utility manages services, which we also covered in the basics course, followed by restart, and then the service name Docker. Hit enter. Perfect. There's one more magic command we need, which refreshes the information on user group memberships. This command looks like new grp docker. And just like that, we've done everything. All these steps were to avoid typing sudo docker and whatever you need after that. So now, we can write the same commands, but without the sudo prefix. Drumroll? Let's try it, and it all works. In the first Docker lesson, those commands returned an error because they required root permissions. Right now, everything is running smoothly. We've got everything set up. Let's talk a bit about the documentation. On the official Docker website, it says, if you want to check out the documentation for Docker containers, you can run a container that holds the documentation. It's a recursive approach, you see. If you want documentation on containers, you simply run the documentation container. But there's no need to worry about that. It's really not complicated at all. We'll just need one single command. And it looks like this. Docker run, which means we're launching a specific container called docker/getting started. The only catch is, we need to run it with certain options. I'll just write those options down now and I'll explain them a bit later. They are -d, -p, and then we write 80:80. So we run our command like this. Of course, as usual, we're told that the image cannot be found locally, so it's downloading now. Where from? Docker Hub, of course. The image has been downloaded, and at the same time the container should have started up. Let's check with the command docker ps. Great! The command docker ps shows us that we have one container, and it's called getting started, and it's currently running. At this large font size, we can't see the entire line, but it's actually all about one container. If we reduce the font, it's clearer. But I've enlarged it for you so the information is easier to digest. So we have this running documentation container. How can we view this documentation? Here's a little secret. We launched our container with certain flags to forward the ports, and in the information about the Docker container, it's listed that it's accessible on port 80. So what's port 80? That's generally for HTTP requests. This means that we can go to our web browser, since we're on Ubuntu with a graphical interface, and type in something like localhost:80. And there we go, we see a little website with information about Docker. There are various pages on it. Now, where did this website come from? We didn't install any web server, neither Nginx nor Apache. Nothing is set up on our machine. But this site is housed within the Docker container. So if I stop this container right now, the site will cease to exist. Check this out. I type docker stop, and then I can pass the container ID, which you can see in the first column. I'll copy that, paste it, and hit enter. Let's check again. No running containers anymore. Docker ps doesn't show us anything else. I refresh the page in the browser, and there's nothing to see. We stopped the container. That means the local internal website with the documentation is gone too, but we can quickly restart it. Just run docker run again, refresh, and everything works again. I highly recommend that you set up this documentation container on your own machine and browse through its pages, at least to get a rough idea of the fundamental concepts and basic capabilities of Docker, so you make your introduction to it easier. All of the previous container examples we've just run were pretty simple and more focused on learning. So now, let's try to launch something that's closer to real working conditions. How about a web server in a Docker container? From the popular web servers, we know about Nginx and Apache. Let's check Docker Hub and see if there's an Nginx image available. We can type docker search Nginx, and sure enough, we get a list of images. At the top of the list is the official Nginx web server image. By the way, it's important that the image is official because otherwise, you never know who might have uploaded something here for public access. It's always safer to rely on official builds. Great! Now that we've found the image we need, let's download it to our machine. The command docker images will show us the list of images that we currently have locally. Right now, we have 2 images. These are the images for the containers we've run previously, which got downloaded along the way. Now, let's fetch the Nginx image as well. We'll use the command docker pull for that. And we just specify the image name. Nginx, press enter. The image takes up some space on the disk, so downloading it might not be instantaneous. Awesome! The command has completed successfully. Let's check the list of our local images again, and we see that the Nginx web server image has been added here. Time to launch it. We'll run docker run nginx. That seems correct. When we hit enter, something does start up. But how do we work with this? Look at that. The cursor is blinking, and we didn't get a prompt to enter commands. We can't even interact in this terminal window anymore. So, we need to run our container a little differently. Let's stop the current container using the keyboard shortcut Ctrl-C, and we'll start it again with the -d option, which means detached, or essentially running the process in the background, disconnecting it from our terminal. Pressing enter now gives us a command prompt back. At the same time, docker ps shows that we even have 2 running containers, the previous getting started and our Nginx, to avoid cluttering our workspace with the previous getting started container. Let's stop it. We can use docker stop and either specify the container ID or the name listed in the last column. Just like that. Let's check. Now, docker ps shows only 1 running container, which is our Nginx web server. But what's the problem now? Well, we didn't leave any interfaces for interacting with the web server. In other words, we should have mapped a port. So let's stop it again. We'll type docker stop and provide the container ID. And let's confirm. Yes, we've stopped everything. Now we're going to restart our container, but add the -b option, which stands for port. This allows us to map a port. The syntax is that after the -p option, we specify a port number, let's say 8123. Then we write a colon, and after that, we also provide a port number, but this one will be inside the container. So, the first number that you see before the colon is the port number on the outside of the container. That's the one we'll use to access it. The number after the colon represents the port number inside the container. Essentially, that's where we'll actually get responses from. Let's take another look at the list of running containers. Notice how in the ports column, it shows that port number 8123 is mapped to port number 80 inside the container. This means we've forwarded the port, allowing us to connect to it and see what response we get. In your browser, you type localhost :8123, and then you'll see welcome to Nginx. When we see a page like this, it means the Nginx web server is running, but hasn't been configured at all. It's just up with default settings, which is basically a standard placeholder showing us that it works. Now, the next question is, how do we control this Nginx web server? If we try to find Nginx directly on our machine, we'll realize there's no such web server installed here. And that's correct because Nginx is running inside the container. So, to get to the web server and manage it, we need to step inside the container. There, we'll find all the Nginx infrastructure. Let's do a simple example and replace that page. We can return some of our own text, perhaps different HTML markup. So, what's the plan? In Docker documentation, we encountered the exec command, which means execute. This command lets you run any command inside a running Docker container. And with this exec command, we're going to work some magic. First, let's find our container's name. Got it? Let's copy that. Now we run the command docker exec. Next, we provide the name of our container. And what are we going to run? Let's say we want a bash terminal /bin/bash. Just a couple of important flags we need, -i and -t. Hit enter, and what do we see? Notice how the command prompt has changed. If I type who am I, it will tell me I'm root. If I type ls, I'll see some kind of file system. If I type in nginx-t, it will show me the nginx configurations. So, using the exec command, we've dove into the container and found the nginx web server. Now we can control it right from here. We wanted to modify the web page. The page being displayed here is called index.html. If we've forgotten where it's located, that's no big deal. We can use the find command to locate it. Starting from the root, we'll search for the file by name. We use the -name flag and add index.html. There it is. That's the path to our file. We can copy it. Let's use the cat command to print the contents of our file to the screen. And here's the text we see. Welcome to nginx, if you see this page. And so on. That's the very text we see here. Great! What's our next step? We'll delete this file. Just rm and poof, it's gone. Now, let's recreate it. Let's use the cat command, followed by the right arrow, the file name, and then enter our markup. We use the h1 tag and some text. Now, let's close the h1 tag. Press Ctrl D to finish the cat command. We can check the contents of the file again. Yes, now it has our new text. Let's go back to the browser and try refreshing the page. Press Ctrl F5 to ensure it's not showing from the cache, and let's enjoy the fact that everything worked out. In other words, we were able to manage the nginx web server running inside a Docker container. If we type exit, we'll leave the container, but continue working in our terminal. Meanwhile, Docker PS will show that our container is still running, everything is fine, and it's functioning properly. We can refresh the page in the browser, and everything is still good there. It seems like we've covered the entire Docker infrastructure and its components, but there's one more element we need to talk about, and that's the Docker file. So, what exactly is a Docker file? Let's dive in. First and foremost, a Docker file is just a plain text file that has to be named exactly Docker file. It's crucial that the first letter is uppercase and the rest are lowercase. The reason we have this Docker file is that in it, we can write some instructions that will allow us to create an image later on. And from that image, we can then run our containers. In fact, from one image, we can launch several containers at once, even simultaneously. Let's remember that an image is just a file sitting on a disk, a binary file, basically a hefty file, whereas a container is an application that's already up and running. Now, what kind of instructions can we write in a Docker file? Let's take a look at the official Docker documentation. I'll leave a link in the lesson notes, and we can check out the list of those instructions. Here it is. It's not too long, really. It's a limited set of directives, so to speak. Right now, let's set up our windows so that we can see both the list of instructions and write our own Docker file at the same time. Before we start, let's create a separate folder for our Docker file. We'll make a directory called nginx project because, as you might have guessed, our ultimate goal is to build a web server, nginx, from this Docker file. Now let's navigate to our new folder and create a file with the name we need. For simplicity, we'll use the nano editor. So, what instructions do we write in a Docker file? We'll start with the from directive. From Let's specify what's called the base image, and we need to sketch out an explanation here. To clarify what the from directive means and what a base image is, let's imagine this scenario. Let's say we have a Docker image with Linux Ubuntu. We use it, access this Docker image, and launch our containers from it. Life is good, everything is fine. At some point, we notice that whenever we run containers from this image, we often have to install a web server. Let's say it's nginx. This means we have a routine task that keeps popping up, so we manually install nginx in our running container. However, thanks to the from directive, we can create a new image based on our existing Ubuntu Linux image. We can later add the nginx web server to it, and it will become its own image. We can also access that image and run containers from it, and everything will work smoothly. Then we notice that we are happily using the nginx image, running containers from it, but we find ourselves repeatedly having to set up some web application. Let's call it web app. This is a routine operation too, and of course, we want to simplify and automate this task as well. Once again, we can create a new image based on our current nginx image. This will be an independent image, and we will use it to run our own containers. You won't have to manually install this application every time. Then, based on this image, we might want to create another image, building another image off that one. Each image can have some add-ons. At the same time, each image will be independent. We'll run our containers from it and live happily. This is how we can think about the idea of a layered cake, if you will, when one image can reference a certain base image. That reference is indicated by the directive from. So, after the word from in the Docker file, we can specify a base image. In our case, let's say it will be Debian. Next, we can add a colon and specify a version, or we can simply leave it out, not specify anything, and the latest version will be used. That's the from directive. We obviously can go through all the directives together, but you can check them out on your own if you're interested. Right now, we're going to focus only on the ones that we'll need for our project. Next, we're going to write the directive called maintainer. So, after the word maintainer, we indicate the author or owner of the image. Here, we could write the name of our company or our personal name. Let's go with pragmatic programmer. Now, we'll write the run directive. As you may have noticed, the names of directives are written in uppercase. The run directive allows us to specify a command that will be executed during the image creation process. If we go back to the diagram we drew, the command described in the run directive will be executed at that specific point in time. So we'll write apt get update. That's the command we want to run. Additionally, you can have multiple run instructions in a Docker file. For the second run, we'll enter the next command. It's also apt-get, but now we'll use install and then nginx. What we want to do is install the nginx web server. Let's add the -y flag. So, in essence, this third line is quite necessary to prepare the installation of nginx. Also, let's pay attention to the -y flag, which helps to avoid prompts during installation. In our lessons on package managers, specifically apt and opt-get, we mentioned that the -y flag is convenient to use, so you won't be asked about anything during installation. In this case, the -y flag is even more important because we want to write a script in this Docker file, and we want that script to run without any interaction from us. So, it's crucial not to forget about the -y flag. The next directive we'll use is volume. This lets us create a mount point, where we can later connect a folder from the host machine. In our example, we'll specify the path to the folder as /var/www/html. That's the standard path for the nginx web server. Next, we'll write the line expose 80. What does that mean? The expose directive prepares for port forwarding. Since we plan to deploy a web server from this Docker file, it makes sense to prepare port 80 so that we can forward it to our container later. we also need another directive called cmd. Let's write a command and then comment on it. We'll write an instruction that effectively starts the Nginx web server with a specified set of parameters. Now, the cmd and run directives are somewhat similar because they both allow you to specify commands that will be executed at certain points. The key difference is that the commands in the run directives are executed during image creation. On the other hand, commands in cmd are executed when the container itself starts, meaning later in the process. Also, you can only write one command in cmd, while you can have multiple run instructions. Each of these run instructions, in turn, creates another layer. What other instructions are there that we haven't used yet, but might be useful and interesting in general? For example, let's talk about the commands add and copy. These are similar directives. They allow you to copy files or folders from your host machine into a container. However, the add directive also has the capability to unpack archives and can accept a URL as input. The entry point directive sets a base directory where we'll be working by default. You can also pass arguments to it. The user directive lets you specify the user ID and the group. Meanwhile, workdir allows you to set the directory for subsequent instructions. So, we've written our version of the Docker file. In Nano, we press the keyboard shortcuts Ctrl-O and Ctrl-X to save and exit. We see our file. We can display its contents on the screen. Great! So, we have created a Docker file with a certain set of instructions. Now, we'll use this file to build an image. First, let's take a look at the list of images we have on our machine. We've got 1, 2, 3. We're going to create another one. The command docker build allows us to do that. We type docker build. After that, we come up with a name for our image. Let's call it my Nginx image. Next, we specify the folder where the Docker file is located. In this case, we can just use a dot or // because we are already in the same directory where our Docker file is. And we also need to add the -t flag to this command. Now let's go ahead and run it. As we execute the docker build command, it essentially processes the instructions we left in our Docker file. Watch this. Step 1. From Debian, just like we wrote. Step 2. Specifying the maintainer. Step 3. The run directive. Step 4. Again run, and so on. When we get back to the command prompt, it means all our steps have completed successfully. As a result of running the build command, we should have a new image. Before running this command, we noticed we had 3 images. Now we've created one more. Let's check again how many images we have now. There were 3, we added 1, and now we have 5. Basic arithmetic. If anyone notices the twist, why did 3 plus 1 equal 5? Feel free to drop a comment about that. But, of course, we'll discuss that point too. To clarify, let's display the contents of our Docker file and take a look at the very first line. From Debian, this means we've specified a base image of Debian. That's our dependency. We created our new my Nginx image based on the Debian image. And since we didn't already have the Debian image on our machine, it was downloaded in the process. And here it is. Thus, in our scenario, 2 new images were created from the Docker file. One is Debian, our dependency, and the other is my Nginx image, which we created. All our dependencies need to be on our machine. That's why 2 images were created. Another important detail to note. The my Nginx image we created occupies 153 megabytes on disk. In contrast, the Docker file we used to create it is just 163 bytes. Not kilobytes, not megabytes, just 163 bytes. Can you feel the difference? It's a million times different. That's why we mentioned that a Docker file is a compact way to store instructions for running containers later on. But we can't launch a container directly from a Docker file. We need an intermediate state known as an image. From the image, we can then run the container. However, the image itself takes up significantly more space on the disk. Now that we've created our image, let's go ahead and run a container from it. Remember, we use the command docker run my nginx image. That's the name of our image. And don't forget the important flags. -d detach. This frees up the command line for further inputs. -p. This is for port mapping. Let's have port 9000 on the outside map to port 80 inside the container. You can choose any available port on the outside that you like, but inside, we'll specifically use port 80. This is because, first, we've prepared this port in the Docker file. And secondly, the nginx web server uses port 80 inside the container. So, let's run our command. Press enter. Great. Now, let's check with docker ps. We see that a new container has appeared on port 9000. You can open your browser, type in localhost 9000, and you'll see the greeting from the nginx web server again. Task completed. And that's how we've easily deployed a container with an nginx web server, using instructions we wrote in the Docker file. Let's talk about one more final piece of Docker's infrastructure in our brief overview, which is called Docker Compose. First of all, it's important to note that Docker Compose doesn't come packaged with Docker by default, so you need to install it separately. For instance, you can use the command sudo apt install Docker Compose. After installation, we'll call up the help again to make sure the package installed correctly. Great. Now, let's dive into Docker Compose. On one hand, it somewhat mirrors or duplicates the functionalities of Docker itself, including the Docker file. But in reality, Docker Compose allows us to implement scenarios that are far more complex than what you can do with just a Docker file. In general, you could say that Docker Compose is a tool for orchestrating a large number of containers. The thing is, in real-world working conditions, admins, system administrators, and other DevOps professionals have to deal with a lot of containers, and they need a way to manage all these containers in a consistent manner. This involves a lot of routine work, and when the routine becomes overwhelming, as we all know, superhero programmers step in. They suggest automating these tasks as much as possible. That's where tools like Docker Compose come into play, and there's also a more complex and popular tool called Kubernetes. You could say that Docker Compose is like a lightweight version of Kubernetes. Let's take a specific, relatively simple example to explore what Docker Compose can do. We're going to create a WordPress website project with just a few simple steps. First, let's create a folder for our project. Make directory WordPress site. Now, we'll navigate into that folder. It's currently empty. Inside this folder, we'll create a file called dockercompose.yml. The YML extension is usually pronounced as YAML. This is a type of text file format where we write instructions in the form key:value. Let's give an example. The Smart Editor Nano gives us nice syntax highlighting right away. Now, let's mention an important aspect of YAML file syntax. As we mentioned, here we write key-value pairs separated by a colon. In this format, indentation is crucial. You need to be mindful of spaces. It indicates levels of nesting. If you don't maintain the correct spacing, the syntax will break, and as a result, the project won't start. In this example, we want to build and run two containers, WordPress and MariaDB. Here we have the settings for WordPress, and below them, we'll have the settings for the MariaDB project. As you may know, MariaDB is a fork of the MySQL server. When Oracle acquired the rights to MySQL, the MySQL development team made an agreement to keep the project as it was while retaining the rights to develop it as they saw fit. That's why MariaDB is an offshoot of MySQL. In a sense, you could say we're writing a kind of Docker file here. The only difference is that there are more options available and the syntax is a bit more complex. You can actually run multiple projects by describing them in a single file. So, our first project is called WordPress. The image tells us this. We already know this term in the context of Docker. This is a basic image. The image is also called WordPress. So, the container we're going to build will be based on the WordPress image. The keyword links allows us to set up links. In this case, it's linking to MariaDB, which is our second project. The environment section lets us define various parameters, environment variables, logins, passwords, and so on. Ports works just like in a Docker file and allows us to expose ports. Volumes also work similarly to Docker files, exposing directories. The syntax is such that we first write the directory on our host machine, then a colon, and then the directory inside the container. Next, there will be similar instructions for the MariaDB project. So, we have a straightforward Docker Compose YAML file here. We save it and exit. Here it is. Now, with just one command, we can start all our projects. Let's start with Docker PS to ensure we don't have any running containers at the moment. Next, we'll check the list of images we currently have. Now, let's run Docker Compose. We type sudo docker compose up, just one simple command. The -d option, which means detach, is also nice to use. Here we go. We hit enter. Now, our Docker Compose YAML file is being processed. Again, similar to Docker files. However, in this latest example, we have a lot more instructions, and the logic is a bit more complex, so the build will take longer. But at least we start multiple containers with just one command. The required images will be downloaded along the way, and the entire infrastructure will be set up. When we get command line access back, it means everything has been set up. Now, let's see what we have. Running Docker PS shows us that we have 2 running containers. In one of those containers, we've exposed port 80, as specified in the YAML file settings. And running Docker images will show us the new images we just downloaded. These are MariaDB and WordPress. So, we now have a container with port 80 exposed. Port 80, as we know, is used for HTTP requests. This means we can check what our browser shows. We type this address, localhost:80. Actually, since port 80 is a default, you don't have to specify it. But we do for clarity. It presents us with a certain interface. Here we are prompted to select a language. We choose one and hit continue. On the next step, we can set the site name, username, password, and email. We click the install WordPress button. We can save the password, and now we click login. We log in, and what do we see? We see the WordPress site admin panel. This is the website itself, the administrative panel. We can manage it. All of this runs inside our container. So, if we stop this container, the site will stop working too. So, with this set of instructions, we successfully launched a WordPress site inside a Docker container using the Docker Compose tool. Overall, we've looked at the key elements of Docker's infrastructure, its components, and how it operates. Now, let's take a look at what's left behind after we're done. We remember that the command docker ps shows us a list of running containers. But if we add the -a flag to this command, we should get a list of all containers that have been started recently. And in our case, that list is significantly longer. I think you can imagine how many lines that list could have accumulated over a week or a month of work. So, it's a good idea to clean up the main history. And we know there's a command for that. Docker rm, which stands for remove, which asks us to specify the container ID. In that case, it gets deleted and we see that there's one line less now. When we use Docker rm and pass the ID, we get an error, the second time for some reason. That's because we mentioned earlier that a running container can't be deleted. In this case, it's in the up state and currently operational. So, to delete that container, we first need to stop it. This means we start with docker stop for our container. Only after that can we run docker rm to successfully remove it. Alternatively, we can force delete a running container. Using docker rm, the container ID, and the -f flag, which means force, we can remove it forcefully. In this case, it worked. But in any event, manually deleting 100 or more containers one by one isn't a very appealing prospect. We'd like to find a way to delete them all in one go with one command. And actually, we do have that option. We can write a simple one-liner script to take care of all the work at once. What do we need to write for that? If we add the -q flag to the last command docker ps-a, it will only return the container IDs. Now, we wrap our command in parentheses and place a $sign before the parentheses. Then, before the entire command, we write docker rm. This means we want to execute docker rm for each line that the command in parentheses returns. In other words, for each of those IDs. Let's give it a try. Hit enter. The command executed. Now let's check docker ps-a again. And we see that we've successfully cleaned up the history. The history of running containers. You can also delete images in a similar way. Docker images will give us a list of the images present on our local machine. And we have the docker rmi command, which stands for remove image. For this command, we need to provide either the name of our image or its ID. Just like that. And now we see that the specified images have been removed. In general, you can create a similar one-liner script to remove all images. But there's less need for that compared to cleaning up the history of running containers. Let's wrap up. In this section, we got acquainted with Docker, a popular tool for containerizing our projects. We discussed Docker's infrastructure, its components, images, containers, and Docker Hub. And we learned how to read the documentation. We also set up an Nginx web server in a Docker container. And we got acquainted with the Dockerfile and the Docker Compose utility.